Hello and welcome to Machine Learning with Python. In this course, you'll learn how machine learning is used in many key fields and industries. For example, in the healthcare industry, data scientists use machine learning to predict whether a human cell that is believed to be at risk of developing cancer is either benign or malignant. As such, machine learning can play a key role in determining a person's health and welfare. You'll also learn about the value of decision trees and how building a good decision tree from historical data helps doctors to prescribe the proper medicine for each of their patients. You'll learn how bankers use machine learning to make decisions on whether to approve loan applications. And you will learn how to use machine learning to do bank customer segmentation, where it is not usually easy to run for huge volumes of varied data. In this course, you'll see how machine learning helps websites such as YouTube, Amazon, or Netflix develop recommendations to their customers about various products or services, such as which movies they might be interested in going to see or which books to buy. There is so much that you can do with machine learning. Here, you'll learn how to use popular Python libraries to build your model. For example, given an automobile dataset, we can use the scikit-learn library to estimate the CO2 emission of cars using their engine size or cylinders. We can even predict what the CO2 emissions will be for a car that hasn't even been produced yet. And we'll see how the telecommunications industries can predict customer churn. You can run and practice the code of all these samples using the built-in lab environment in this course. You don't have to install anything to your computer or do anything on the cloud. All you have to do is click a button to start the lab environment in your browser. The code for the samples is already written using Python language in Jupyter Notebooks, and you can run it to see the results or change it to understand the algorithms better. So what will you be able to achieve by taking this course? Well, by putting in just a few hours a week over the next few weeks, you'll get new skills to add to your resume, such as regression, classification, clustering, scikit-learn, and SciPy. You'll also get new projects that you can add to your portfolio, including cancer detection, predicting economic trends, predicting customer churn, recommendation engines, and many more. You'll also get a certificate in machine learning to prove your competency and share it anywhere you like, online or offline, such as LinkedIn profiles and social media. So let's get started. Hello and welcome. In this video, I will give you a high-level introduction to machine learning. So let's get started. This is a human cell sample extracted from a patient, and this cell has characteristics. For example, its clump thickness is 6, its uniformity of cell size is 1, its marginal adhesion is 1, and so on. One of the interesting questions we can ask at this point is this a benign or malignant cell? In contrast with a benign tumor, a malignant tumor is a tumor that may invade its surrounding tissue or spread around the body, and diagnosing it early might be the key to a patient's survival. One could easily presume that only a doctor with years of experience could diagnose that tumor and say if the patient is developing cancer or not, right? Well, imagine that you've obtained a dataset containing characteristics of thousands of human cell samples extracted from patients who are believed to be at risk of developing cancer. Analysis of the original data showed that many of the characteristics differed significantly between benign and malignant samples. You can use the values of these cell characteristics in samples from other patients to give an early indication of whether a new sample might be benign or malignant. You should clean your data, Select a proper algorithm for building a prediction model, and train your model to understand patterns of benign or malignant cells within the data. Once the model has been trained by going through data iteratively, it can be used to predict your new or unknown cell with rather high accuracy. This is machine learning. It is the way that a machine learning model can do a doctor's task, or at least help that doctor make the process faster. Now, let me give a formal definition of machine learning. Machine learning is the subfield of computer science that gives computers the ability to learn without being explicitly programmed. Let me explain what I mean when I say without being explicitly programmed. Assume that you have a data set of images of animals such as cats and dogs, and you want to have software or an application that can recognize and differentiate them. The first thing that you have to do here is interpret the images as a set of feature sets. For example, does the image show the animal's eyes? If so, what is their size? Does it have ears? What about a tail? How many legs? Does it have wings? Prior to machine learning, each image would be transformed to a vector of features. Then, traditionally, we had to write down some rules or methods in order to get computers to be intelligent and detect the animals. But it was a failure. Why? Well, as you can guess, it needed a lot of rules, highly dependent on the current data set, and not generalized enough to detect out-of-sample cases. This is when machine learning entered the scene. Using machine learning allows us to build a model that looks at all the feature sets and their corresponding type of animals. And it learns the pattern of each animal. It is a model built by machine learning algorithms. It detects without explicitly being programmed to do so. In essence, machine learning follows the same process that a 4-year-old child uses to learn, understand, and differentiate animals. So, machine learning algorithms, inspired by the human learning process, iteratively learn from data and allow computers to find hidden insights. These models help us in a variety of tasks, such as object recognition, summarization, recommendation, and so on. Machine learning impacts society in a very influential way. Here are some real-life examples. First, how do you think Netflix and Amazon recommend videos, movies, and TV shows to its users? They use machine learning to produce suggestions that you might enjoy. This is similar to how your friends might recommend a television show to you based on their knowledge of the types of shows you like to watch. How do you think banks make a decision when approving a loan application? They use machine learning to predict the probability of default for each applicant, and then approve or refuse the loan application based on that probability. Telecommunication companies use their customers' demographic data to segment them, or predict if they will unsubscribe from their company the next month. There are many other applications of machine learning that we see every day in our daily life, such as chatbots, logging into our phones, or even computer games using face recognition. Each of these use different machine learning techniques and algorithms. So let's quickly examine a few of the more popular techniques. The regression estimation technique is used for predicting a continuous value. For example, predicting things like the price of a house based on its characteristics, or to estimate the CO2 emission from a car's engine. A classification technique is used for predicting the class or category of a case. For example, if a cell is benign or malignant, or whether or not a customer will churn. Clustering groups of similar cases, for example, can find similar patients, or can be used for customer segmentation in the banking field. Association technique is used for finding items or events that often co-occur. For example, grocery items that are usually bought together by a particular customer. Anomaly detection is used to discover abnormal and unusual cases. For example, it is used for credit card fraud detection. Sequence mining is used for predicting the next event, for instance, the clickstream in websites. Dimension reduction is used to reduce the size of data. And finally, recommendation systems. This associates people's preferences with others who have similar tastes and recommends new items to them, such as books or movies. We will cover some of these techniques in the next videos. By this point, I'm quite sure this question has crossed your mind. What is the difference between these buzzwords that we keep hearing these days, such as artificial intelligence or AI, machine learning, and deep learning? Well, let me explain what is different between them. In brief, AI tries to make computers intelligent in order to mimic the cognitive functions of humans. So, artificial intelligence is a general field with a broad scope, including computer vision, language processing, creativity, and summarization. Machine learning is the branch of AI that covers the statistical part of artificial intelligence. It teaches the computer to solve problems by looking at hundreds or thousands of examples, learning from them, and then using that experience to solve the same problem in new situations. And deep learning is a very special field of machine learning, where computers can actually learn and make intelligent decisions on their own. Deep learning involves a deeper level of automation in comparison with most machine learning algorithms. Now that we've completed the introduction to machine learning, subsequent videos will focus on reviewing two main components. First, you'll be learning about the purpose of machine learning and where it can be applied in the real world. And second, you'll get a general overview of machine learning topics, such as supervised versus unsupervised learning, model evaluation, and various machine learning algorithms. So now that you have a sense of what's in store on this journey, let's continue our exploration of machine learning. Thanks for watching. Hello and welcome. In this video, we'll talk about how to use Python for machine learning. So let's get started. Python is a popular and powerful general-purpose programming language that recently emerged as the preferred language among data scientists. You can write your machine learning algorithms using Python, and it works very well. However, there are a lot of modules and libraries already implemented in Python that can make your life much easier. We try to introduce the Python packages in this course and use it in the labs to give you better hands-on experience. The first package is NumPy, which is a math library to work with n-dimensional arrays in Python. It enables you to do computation efficiently and effectively. It is better than regular Python because of its amazing capabilities. For example, for working with arrays, dictionaries, functions, data types, and working with images, you need to know NumPy. SciPy is a collection of numerical algorithms and domain-specific toolboxes, including signal processing, optimization, statistics, and much more. SciPy is a good library for scientific and high-performance computation. Matplotlib is a very popular plotting package that provides 2D plotting as well as 3D plotting. Basic knowledge about these three packages, which are built on top of Python, is a good asset for data scientists who want to work with real-world problems. If you're not familiar with these packages, I recommend that you take the Data Analysis with Python course first. This course covers most of the useful topics in these packages. Pandas library is a very high-level Python library that provides high-performance, easy-to-use data structures. It has many functions for data importing, manipulation, and analysis. In particular, it offers data structures and operations for manipulating numerical tables and time series. Scikit-learn is a collection of algorithms and tools for machine learning, which is our focus here, and which you'll learn to use within this course. As we'll be using scikit-learn quite a bit in the labs, let me explain more about it and show you why it is so popular among data scientists. Scikit-learn is a free machine learning library for the Python programming language. It has most of the classification, regression, and clustering algorithms, and it's designed to work with the Python numerical and scientific libraries, NumPy and SciPy. Also, it includes very good documentation. On top of that, implementing machine learning models with scikit-learn is really easy with a few lines of Python code. Most of the tasks that need to be done in a machine learning pipeline are implemented already in scikit-learn, including pre-processing of data, feature selection, feature extraction, train-test splitting, defining the algorithms, fitting models, tuning parameters, prediction, evaluation, and exporting the model. Let me show you an example of how scikit-learn looks like when you use this library. You don't have to understand the code for now, but just see how easily you can build a model with just a few lines of code. Basically, machine learning algorithms benefit from standardization of the dataset. If there are some outliers or different scales fields in your dataset, you have to fix them. The pre-processing package of scikit-learn provides several common utility functions and transformer classes to change raw feature vectors into a suitable form of vector for modeling. You have to split your dataset into train and test sets to train your model, and then test the model's accuracy separately. Scikit-learn can split arrays or matrices into random train and test subsets for you in one line of code. Then you can set up your algorithm. For example, you can build a classifier using a support vector classification algorithm. We call our estimator instance CLF and initialize its parameters. Now you can train your model with the train set. By passing our training set to the fit method, the CLF model learns to classify unknown cases. Then we can use our test set to run predictions. And the result tells us what the class of each unknown value is. Also, you can use the different metrics to evaluate your model accuracy, for example, using a confusion matrix to show the results. And finally, you save your model. You may find all or some of these machine learning terms confusing, but don't worry. We'll talk about all of these topics in the following videos. The most important point to remember is that the entire process of a machine learning task can be done simply in a few lines of code using scikit-learn. Please notice that though it is possible, it would not be that easy if you want to do all of this using NumPy or SciPy packages. And of course, it needs much more coding if you use pure Python programming to implement all of these tasks. Thanks for watching. Hello and welcome. In this video, we'll introduce supervised algorithms versus unsupervised algorithms. So let's get started. An easy way to begin grasping the concept of supervised learning is by looking directly at the words that make it up. Supervise means to observe and direct the execution of a task, project, or activity. Obviously, we aren't going to be supervising a person. Instead, we'll be supervising a machine learning model that might be able to produce classification regions like we see here. So, how do we supervise a machine learning model? We do this by teaching the model. That is, we load the model with knowledge so that we can have it predict future instances. But this leads to the next question, which is, how exactly do we teach a model? We teach the model by training it with some data from a labeled dataset. It's important to note that the data is labeled. And what does a labeled dataset look like? Well, it could look something like this. This example is taken from the cancer dataset. As you can see, we have some historical data for patients, and we already know the class of each row. Let's start by introducing some components of this table. The names up here, which are called clump thickness, uniformity of cell size, uniformity of cell shape, marginal adhesion, and so on, are called attributes. The columns are called features, which include the data. If you plot this data and look at a single data point on a plot, it'll have all of these attributes. That would make a row on this chart, also referred to as an observation. Looking directly at the value of the data, you can have two kinds. The first is numerical. When dealing with machine learning, the most commonly used data is numeric. The second is categorical. That is, it's non-numeric because it contains characters rather than numbers. In this case, it's categorical because this dataset is made for classification. There are two types of supervised learning techniques. They are classification and regression. Classification is the process of predicting a discrete class label or category. Regression is the process of predicting a continuous value as opposed to predicting a categorical value in classification. Look at this dataset. It is related to CO2 emissions of different cars. It includes engine size, cylinders, fuel consumption, and CO2 emission of various models of automobiles. Given this dataset, you can use regression to predict the CO2 emission of a new car by using other fields such as engine size or number of cylinders. Since we know the meaning of supervised learning, what do you think unsupervised learning means? Yes, unsupervised learning is exactly as it sounds. We do not supervise the model, but we let the model work on its own to discover information that may not be visible to the human eye. It means the unsupervised algorithm trains on the dataset and draws conclusions on unlabeled data. Generally speaking, unsupervised learning has more difficult algorithms than supervised learning, since we know little to no information about the data, or the outcomes that are to be expected. Dimension reduction, density estimation, market basket analysis, and clustering are the most widely used unsupervised machine learning techniques. Dimensionality reduction and/or feature selection play a large role in this by reducing redundant features to make the classification easier. Market basket analysis is a modeling technique based upon the theory that if you buy a certain group of items, you're more likely to buy another group of items. Density estimation is a very simple concept that is mostly used to explore the data to find some structure within it. And finally, clustering. Clustering is considered to be one of the most popular unsupervised machine learning techniques used for grouping data points or objects that are somehow similar. Cluster analysis has many applications in different domains, whether it be a bank's desire to segment its customers based on certain characteristics, or helping an individual to organize and group his or her favorite types of music. Generally speaking, though, clustering is used mostly for discovering structure, summarization, and anomaly detection. So, to recap, the biggest difference between supervised and unsupervised learning is that supervised learning deals with labeled data, while unsupervised learning deals with unlabeled data. In supervised learning, we have machine learning algorithms for classification and regression. In unsupervised learning, we have methods such as clustering. In comparison to supervised learning, unsupervised learning has fewer models and fewer evaluation methods that can be used to ensure that the outcome of the model is accurate. As such, unsupervised learning creates a less controllable environment as the machine is creating outcomes for us. Thanks for watching. Hello and welcome. In this video, we'll be giving a brief introduction to regression. So let's get started. Look at this data set. It's related to CO2 emissions from different cars. It includes engine size, number of cylinders, fuel consumption, and CO2 emission from various automobile models. The question is, given this data set, can we predict the CO2 emission of a car using other fields, such as engine size or cylinders? Let's assume we have some historical data from different cars, and assume that a car, such as in row 9, has not been manufactured yet, but we're interested in estimating its approximate CO2 emission after production. Is it possible? We can use regression methods to predict a continuous value such as CO2 emission using some other variables. Indeed, regression is the process of predicting a continuous value. In regression, there are two types of variables, a dependent variable and one or more independent variables. The dependent variable can be seen as the state, target, or final goal we study and try to predict. And the independent variables, also known as explanatory variables, can be seen as the causes of those states. The independent variables are shown conventionally by X, and the dependent variable is notated by Y. A regression model relates Y, or the dependent variable, to a function of X, i.e., the independent variables. The key point in the regression is that our dependent value should be continuous and cannot be a discrete value. However, the independent variable or variables can be measured on either a categorical or continuous measurement scale. So, what we want to do here is to use the historical data of some cars using one or more of their features and, from that data, make a model. We use regression to build such a regression estimation model. Then the model is used to predict the expected CO2 emission for a new or unknown car. Basically, there are two types of regression models, simple regression and multiple regression. Simple regression is when one independent variable is used to estimate a dependent variable. It can be either linear or nonlinear. For example, predicting CO2 emission using the variable of engine size. Linearity of regression is based on the nature of relationship between independent and dependent variables. When more than one independent variable is present, the process is called multiple linear regression. For example, predicting CO2 emission using engine size and the number of cylinders in any given car. Again, depending on the relation between dependent and independent variables, it can be either linear or nonlinear regression. Let's examine some sample applications of regression. Essentially, we use regression when we want to estimate a continuous value. For instance, one of the applications of regression analysis could be in the area of sales forecasting. You can try to predict a salesperson's total yearly sales from independent variables such as age, education, and years of experience. It can also be used in the field of psychology, for example, to determine individual satisfaction based on demographic and psychological factors. We can use regression analysis to predict the price of a house in an area based on its size, number of bedrooms, and so on. We can even use it to predict employment income for independent variables such as hours of work, education, occupation, sex, age, years of experience, and so on. Indeed, you can find many examples of the usefulness of regression analysis in these and many other fields or domains, such as finance, healthcare, retail, and more. We have many regression algorithms. Each of them has its own importance and a specific condition to which their application is best suited. And while we've covered just a few of them in this course, it gives you enough base knowledge for you to explore different regression techniques. Thanks for watching. Hello and welcome. In this video, we'll be covering linear regression. You don't need to know any linear algebra to understand topics in linear regression. This high-level introduction will give you enough background information on linear regression to be able to use it effectively on your own problems. So, let's get started. Let's take a look at this data set. It's related to the CO2 emission of different cars. It includes engine size, cylinders, fuel consumption, and CO2 emissions for various car models. The question is, given this data set, can we predict the CO2 emission of a car using another field such as engine size? Quite simply, yes. We can use linear regression to predict a continuous value, such as CO2 emission, by using other variables. Linear regression is the approximation of a linear model used to describe the relationship between two or more variables. In simple linear regression, there are two variables, a dependent variable and an independent variable. The key point in the linear regression is that our dependent value should be continuous and cannot be a discrete value. However, the independent variables can be measured on either a categorical or continuous measurement scale. There are two types of linear regression models. They are simple regression and multiple regression. Simple linear regression is when one independent variable is used to estimate a dependent variable. For example, predicting CO2 emission using the engine size variable. When more than one independent variable is present, the process is called multiple linear regression. For example, predicting CO2 emission using engine size and cylinders of cars. Our focus in this video is on simple linear regression. Now, let's see how linear regression works. Okay, so let's look at our data set again. To understand linear regression, we can plot our variables here. We show engine size as an independent variable and emission as the target value that we would like to predict. A scatter plot clearly shows the relation between variables where changes in one variable explain or possibly cause changes in the other variable. Also, it indicates that these variables are linearly related. With linear regression, you can fit a line through the data. For instance, as the engine size increases, so do the emissions. With linear regression, you can model the relationship of these variables. A good model can be used to predict what the approximate emission of each car is. How do we use this line for prediction now? Let us assume for a moment that the line is a good fit of the data. We can use it to predict the emission of an unknown car. For example, for a sample car with engine size 2.4, you can find the emission is 214. Now, let's talk about what the fitting line actually is. We're going to predict the target value y, in our case using the independent variable engine size, represented by x1. The fit line is shown traditionally as a polynomial. In a simple regression problem, a single x, the form of the model would be theta 0 plus theta 1 x1. In this equation, y hat is the dependent variable or the predicted value, and x1 is the independent variable. Theta 0 and theta 1 are the parameters of the line that we must adjust. Theta 1 is known as the slope or gradient of the fitting line, and theta 0 is known as the intercept. Theta 0 and theta 1 are also called the coefficients of the linear equation. You can interpret this equation as y hat being a function of x1 or y hat being dependent of x1. Now the questions are, how would you draw a line through the points, and how do you determine which line fits best? Linear regression estimates the coefficients of the line. This means we must calculate theta 0 and theta 1 to find the best line to fit the data. This line would best estimate the emission of the unknown data points. Let's see how we can find this line, or to be more precise, how we can adjust the parameters to make the line the best fit for the data. For a moment, let's assume we've already found the best fit line for our data. Now, let's go through all the points and check how well they align with this line. Best fit here means that if we have, for instance, a car with engine size X1 equals 5.4 and actual CO2 equals 250, its CO2 should be predicted very close to the actual value, which is Y equals 250 based on historical data. But if we use the fit line, or better to say, using our polynomial with known parameters to predict the CO2 emission, it will return y hat equals 340. Now, if you compare the actual value of the emission of the car with what we've predicted using our model, you will find out that we have a 90-unit error. This means our prediction line is not accurate. This error is also called the residual error. So, we can say the error is the distance from the data point to the fitted regression line. The mean of all residual errors shows how poorly the line fits with the whole data set. Mathematically, it can be shown by the equation mean squared error, shown as MSE. Our objective is to find a line where the mean of all these errors is minimized. In other words, the mean error of the prediction using the fit line should be minimized. Let's reword it more technically. The objective of linear regression is to minimize this MSE equation, and to minimize it, we should find the best parameters theta 0 and theta 1. Now, the question is how to find theta 0 and theta 1 in such a way that it minimizes this error. How can we find such a perfect line? Or, said another way, how should we find the best parameters for our line? Should we move the line a lot randomly and calculate the MSE value every time and choose the minimum one? Not really. Actually, we have two options here. Option 1, we can use a mathematic approach, or option 2, we can use an optimization approach. Let's see how we can easily use a mathematic formula to find the theta 0 and theta 1. As mentioned before, theta 0 and theta 1 in the simple linear regression are the coefficients of the fit line. We can use a simple equation to estimate these coefficients. That is, given that it's a simple linear regression with only two parameters, and knowing that theta 0 and theta 1 are the intercept and slope of the line, we can estimate them directly from our data. It requires that we calculate the mean of the independent and dependent, or target columns, from the dataset. Notice that all of the data must be available to traverse and calculate the parameters. It can be shown that the intercept and slope can be calculated using these equations. We can start off by estimating the value for theta 1. This is how you can find the slope of a line based on the data. X bar is the average value for the engine size in our data set. Please consider that we have 9 rows here, rows 0 to 8. First, we calculate the average of x1 and average of y. Then, we plug it into the slope equation to find theta 1. The xi and yi in the equation refer to the fact that we need to repeat these calculations across all values in our dataset, and I refers to the ith value of x or y. Applying all values, we find theta 1 equals 39. It is our second parameter. It is used to calculate the first parameter, which is the intercept of the line. Now, we can plug theta 1 into the line equation to find theta 0. It is easily calculated that theta 0 equals 125.74. So these are the two parameters for the line, where theta 0 is also called the bias coefficient and theta 1 is the coefficient for the CO2 emission column. As a side note, you really don't need to remember the formula for calculating these parameters, as most of the libraries used for machine learning in Python, R, and Scala can easily find these parameters for you. But it's always good to understand how it works. Now, we can write down the polynomial of the line. So, we know how to find the best fit for our data and its equation. Now the question is, how can we use it to predict the emission of a new car based on its engine size? After we found the parameters of the linear equation, making predictions is as simple as solving the equation for a specific set of inputs. Imagine we are predicting CO2 emission, or Y, from engine size, or X, for the automobile in record number 9. Our linear regression model representation for this problem would be y hat equals theta 0 plus theta 1 x1. Or, if we map it to our data set, it would be CO2 emission equals theta 0 plus theta 1 engine size. As we saw, we can find theta 0, theta 1 using the equations that we just talked about. Once found, we can plug in the equation of the linear model. For example, let's use theta 0 equals 125 and theta 1 equals 39. So we can rewrite the linear model as CO2 emission equals 125 plus 39 engine size. Now, let's plug in the 9th row of our data set and calculate the CO2 emission for a car with an engine size of 2.4. So, CO2 emission equals 125 plus 39 times 2.4. Therefore, we can predict that the CO2 emission for this specific car would be 218.6. Let's talk a bit about why linear regression is so useful. Quite simply, it is the most basic regression to use and understand. In fact, one reason why linear regression is so useful is that it's fast. It also doesn't require tuning of parameters. So, something like tuning the k parameter in k nearest neighbors or the learning rate in neural networks isn't something to worry about. Linear regression is also easy to understand and highly interpretable. Thanks for watching this video. Hello and welcome. In this video, we'll be covering model evaluation. So let's get started. The goal of regression is to build a model to accurately predict an unknown case. To this end, we have to perform regression evaluation after building the model. In this video, we'll introduce and discuss two types of evaluation approaches that can be used to achieve this goal. These approaches are train and test on the same dataset and train-test split. We'll talk about what each of these are, as well as the pros and cons of using each of these models. Also, we'll introduce some metrics for accuracy of regression models. Let's look at the first approach. When considering evaluation models, we clearly want to choose the one that will give us the most accurate results. So, the question is, how can we calculate the accuracy of our model? In other words, how much can we trust this model for prediction of an unknown sample using a given dataset and having built a model such as linear regression? One of the solutions is to select a portion of our dataset for testing. For instance, assume that we have 10 records in our dataset. We use the entire dataset for training, and we build a model using this training set. Now, we select a small portion of the dataset, such as row numbers 6 to 9, but without the labels. This set is called a test set, which has the labels, but the labels are not used for prediction and is used only as ground truth. The labels are called actual values of the test set. Now we pass the feature set of the testing portion to our built model and predict the target values. Finally, we compare the predicted values by our model with the actual values in the test set. This indicates how accurate our model actually is. There are different metrics to report the accuracy of the model, but most of them work generally based on the similarity of the predicted and actual values. Let's look at one of the simplest metrics to calculate the accuracy of our regression model. As mentioned, we just compare the actual values, y, with the predicted values, which is noted as y hat for the testing set. The error of the model is calculated as the average difference between the predicted and actual values for all the rows. We can write this error as an equation. So, the first evaluation approach we just talked about is the simplest one: train and test on the same dataset. Essentially, the name of this approach says it all. You train the model on the entire dataset, then you test it using a portion of the same dataset. In a general sense, when you test with a dataset in which you know the target value for each data point, you're able to obtain a percentage of accurate predictions for the model. This evaluation approach would most likely have a high training accuracy and a low out-of-sample accuracy, since the model knows all of the testing data points from the training. What is training accuracy and out-of-sample accuracy? We said that training and testing on the same dataset produces a high training accuracy, but what exactly is training accuracy? Training accuracy is the percentage of correct predictions that the model makes when using the test dataset. However, a high training accuracy isn't necessarily a good thing. For instance, having a high training accuracy may result in an overfit of the data. This means that the model is overly trained to the dataset, which may capture noise and produce a non-generalized model. Out-of-sample accuracy is the percentage of correct predictions that the model makes on data that the model has not been trained on. Doing a train and test on the same dataset will most likely have low out-of-sample accuracy due to the likelihood of being overfit. It's important that our models have high out-of-sample accuracy because the purpose of our model is, of course, to make correct predictions on unknown data. So, how can we improve out-of-sample accuracy? One way is to use another evaluation approach called train-test-split. In this approach, we select a portion of our dataset for training, for example, rows 0 to 5, and the rest is used for testing, for example, rows 6 to 9. The model is built on the training set. Then, the test feature set is passed to the model for prediction. And finally, the predicted values for the test set are compared with the actual values of the testing set. This second evaluation approach is called train-test-split. Train-test-split involves splitting the dataset into training and testing sets, respectively, which are mutually exclusive, after which you train with the training set and test with the testing set. This will provide a more accurate evaluation on out-of-sample accuracy because the testing dataset is not part of the dataset that has been used to train the data. It is more realistic for real-world problems. This means that we know the outcome of each data point in the dataset, making it great to test with. And since this data has not been used to train the model has no knowledge of the outcome of these data points. So, in essence, it's truly out-of-sample testing. However, please ensure that you train your model with the testing set afterwards, as you don't want to lose potentially valuable data. The issue with train-test-split is that it's highly dependent on the data sets on which the data was trained and tested. The variation of this causes train-test-split to have a better out-of-sample prediction than training and testing on the same dataset, but it still has some problems due to this dependency. Another evaluation model, called k-fold cross-validation, resolves most of these issues. How do you fix a high variation that results from a dependency? Well, you average it. Let me explain the basic concept of k-fold cross-validation to see how we can solve this problem. The entire dataset is represented by the points in the image at the top left. If we have k equals 4 folds, then we split up this dataset as shown here. In the first fold, for example, we use the first 25% of the dataset for testing, and the rest for training. The model is built using the training set, and is evaluated using the test set. Then, in the next round, or in the second fold, the second 25% of the dataset is used for testing and the rest for training the model. Again, the accuracy of the model is calculated. We continue for all folds. Finally, the result of all 4 evaluations are averaged. That is, the accuracy of each fold is then averaged, keeping in mind that each fold is distinct, where no training data in one fold is used in another. K-fold cross-validation in its simplest form performs multiple train test splits using the same data set where each split is different. Then, the result is averaged to produce a more consistent out-of-sample accuracy. We wanted to show you an evaluation model that addressed some of the issues we've described in the previous approaches. However, going in depth with k-fold cross-validation model is out of the scope for this course. Thanks for watching. Hello and welcome. In this video, we'll be covering accuracy metrics for model evaluation. So let's get started. Evaluation metrics are used to explain the performance of a model. Let's talk more about the model evaluation metrics that are used for a regression. As mentioned, basically we can compare the actual values and predicted values to calculate the accuracy of a regression model. Evaluation metrics provide a key role in the development of a model as it provides insight to areas that require improvement. We'll be reviewing a number of model evaluation metrics, including mean absolute error, mean squared error, and root mean squared error. But before we get into defining these, we need to define what an error actually is. In the context of regression, the error of the model is the difference between the data points and the trend line generated by the algorithm. Since there are multiple data points, an error can be determined in multiple ways. Mean absolute error is the mean of the absolute value of the errors. This is the easiest of the metrics to understand since it's just the average error. Mean squared error is the mean of the squared error. It's more popular than mean absolute error because the focus is geared more towards large errors. This is due to the squared term exponentially increasing larger errors in comparison to smaller ones. Root mean squared error is the square root of the mean squared error. This is one of the most popular of the evaluation metrics because root mean squared error is interpretable in the same units as the response vector, or y units, making it easy to relate its information. Relative absolute error, also known as residual sum of square, where y bar is a mean value of y, takes the total absolute error and normalizes it by dividing by the total absolute error of the simple predictor. Relative squared error is very similar to relative absolute error, but is widely adopted by the data science community as it is used for calculating R-squared. R-squared is not an error per se, but is a popular metric for the accuracy of your model. It represents how close the data values are to the fitted regression line. The higher the R-squared, the better the model fits your data. Each of these metrics can be used for quantifying of your prediction. The choice of metric completely depends on the type of model, your data type, and domain of knowledge. Unfortunately, further review is out of scope of this course. Thanks for watching. Hello and welcome. In this video, we'll be covering multiple linear regression. As you know, there are two types of linear regression models: simple regression and multiple regression. Simple linear regression is when one independent variable is used to estimate a dependent variable. For example, predicting CO2 emission using the variable of engine size. In reality, there are multiple variables that predict the CO2 emission. When multiple independent variables are present, the process is called multiple linear regression. For example, predicting CO2 emission using engine size and the number of cylinders in the car's engine. Our focus in this video is on multiple linear regression. The good thing is that multiple linear regression is the extension of the simple linear regression model. So, I suggest you go through the simple linear regression video first if you haven't watched it already. Before we dive into a sample dataset and see how multiple linear regression works, I want to tell you what kind of problems it can solve, when we should use it, and specifically what kind of questions we can answer using it. Basically, there are two applications for multiple linear regression. First, it can be used when we would like to identify the strength of the effect that the independent variables have on a dependent variable. For example, does revision time, test anxiety, lecture attendance, and gender have any effect on exam performance of students? Second, it can be used to predict the impact of changes. That is, to understand how the dependent variable changes when we change the independent variables. For example, if we were reviewing a person's health data, a multiple linear regression can tell you how much that person's blood pressure goes up or down for every unit increase or decrease in a patient's body mass index, holding other factors constant. As is the case with simple linear regression, multiple linear regression is a method of predicting a continuous variable. It uses multiple variables, called independent variables, or predictors, that best predict the value of the target variable, which is also called the dependent variable. In multiple linear regression, the target value, y, is a linear combination of independent variables, x. For example, you can predict how much CO2 a car might emit due to independent variables, such as the car's engine size, number of cylinders, and fuel consumption. Multiple linear regression is very useful because you can examine which variables are significant predictors of the outcome variable. Also, you can find out how each feature impacts the outcome variable. And again, as is the case in simple linear regression, if you manage to build such a regression model, you can use it to predict the emission amount of an unknown case, such as record number 9. Generally, the model is of the form y hat equals theta 0 plus theta 1 x1 plus theta 2 x2, and so on, up to theta n xn. Mathematically, we can show it as a vector form as well. This means it can be shown as a dot product of two vectors, the parameters vector and the feature set vector. Generally, we can show the equation for a multidimensional space as theta transposed x, where theta is an n by 1 vector of unknown parameters in a multidimensional space, and x is the vector of the featured sets, as theta is a vector of coefficients and is supposed to be multiplied by x. Conventionally, it is shown as transpose theta. Theta is also called the parameters, or weight vector of the regression equation. Both these terms can be used interchangeably. And x is the feature set, which represents a car. For example, x1 for engine size, or x2 for cylinders, and so on. The first element of the feature set would be set to 1, because it turns the theta 0 into the intercept or bias parameter when the vector is multiplied by the parameter vector. Please notice that theta transposed x in a one-dimensional space is the equation of a line. It is what we use in simple linear regression. In higher dimensions, when we have more than one input, or x, the line is called a plane or a hyperplane, and this is what we use for multiple linear regression. So, the whole idea is to find the best fit hyperplane for our data. To this end, and as is the case in linear regression, we should estimate the values for theta vector that best predict the value of the target field in each row. To achieve this goal, we have to minimize the error of the prediction. Now, the question is, how do we find the optimized parameters? To find the optimized parameters for our model, we should first understand what the optimized parameters are. Then we will find a way to optimize the parameters. In short, optimized parameters are the ones which lead to a model with the fewest errors. Let's assume for a moment that we have already found the parameter vector of our model. It means we already know the values of theta vector. Now we can use the model and the feature set of the first row of our data set to predict the CO2 emission for the first car, correct? If we plug the feature set values into the model equation, we find y hat. Let's say, for example, it returns 140 as the predicted value for this specific row. What is the actual value? Y equals 196. How different is the predicted value from the actual value of 196? Well, we can calculate it quite simply as 196 subtract 140, which of course equals 56. This is the error of our model only for one row, or one car in our case. As is the case in linear regression, we can say the error here is the distance from the data point to the fitted regression model. The mean of all residual errors shows how bad the model is representing the data set. It is called the mean squared error, or MSE. Mathematically, MSE can be shown by an equation. While this is not the only way to expose the error of a multiple linear regression model, it is one of the most popular ways to do so. The best model for our dataset is the one with minimum error for all prediction values. So, the objective of multiple linear regression is to minimize the MSE equation. To minimize it, we should find the best parameters theta. But how? Okay, how do we find the parameter or coefficients for multiple linear regression? There are many ways to estimate the value of these coefficients. However, the most common methods are the ordinary least squares and optimization approach. Ordinary least squares tries to estimate the values of the coefficients by minimizing the mean square error. This approach uses the data as a matrix and uses linear algebra operations to estimate the optimal values for the theta. The problem with this technique is the time complexity of calculating matrix operations, as it can take a very long time to finish. When the number of rows in your dataset is less than 10,000, you can think of this technique as an option. However, for greater values, you should try other, faster approaches. The second option is to use an optimization algorithm to find the best parameters. That is, you can use a process of optimizing the values of the coefficients by iteratively minimizing the error of the model on your training data. For example, you can use gradient descent, which starts optimization with random values for each coefficient, then calculates the errors and tries to minimize it through wise changing of the coefficients in multiple iterations. Gradient descent is a proper approach if you have a large data set. Please understand, however, that there are other approaches to estimate the parameters of the multiple linear regression that you can explore on your own. After you find the best parameters for your model, you can go to the prediction phase. After we found the parameters of the linear equation, making predictions is as simple as solving the equation for a specific set of inputs. Imagine we are predicting CO2 emission, or Y, from other variables for the automobile in record number 9. Our linear regression model representation for this problem would be y hat equals theta transposed x. Once we find the parameters, we can plug them into the equation of the linear model. For example, let's use theta 0 equals 125, theta 1 equals 6.2, theta 2 equals 14, and so on. If we map it to our data set, we can rewrite the linear model as CO2 emissions equals 125 plus 6.2 multiplied by engine size plus 14 multiplied by cylinder, and so on. As you can see, multiple linear regression estimates the relative importance of predictors. For example, it shows cylinder has higher impact on CO2 emission amounts in comparison with engine size. Now, let's plug in the 9th row of our dataset and calculate the CO2 emission for a car with the engine size of 2.4. So, CO2 emission equals 125 plus 6.2 times 2.4 plus 14 times 4, and so on. We can predict the CO2 emission for this specific car would be 214.1. Now let me address some concerns that you might already be having regarding multiple linear regression. As you saw, you can use multiple independent variables to predict a target value in multiple linear regression. It sometimes results in a better model compared to using a simple linear regression, which uses only one independent variable to predict the dependent variable. Now, the question is, how many independent variables should we use for the prediction? Should we use all the fields in our data set? Does adding independent variables to a multiple linear regression model always increase the accuracy of the model? Basically, adding too many independent variables without any theoretical justification may result in an overfit model. An overfit model is a real problem because it is too complicated for your data set and not general enough to be used for prediction. So, it is recommended to avoid using many variables for prediction. There are different ways to avoid overfitting a model in regression. However, that is outside the scope of this video. The next question is, should independent variables be continuous? Basically, categorical independent variables can be incorporated into a regression model by converting them into numerical variables. For example, given a binary variable such as car type, the code dummies 0 for manual and 1 for automatic cars. As a last point, remember that multiple linear regression is a specific type of linear regression. So, there needs to be a linear relationship between the dependent variable and each of your independent variables. There are a number of ways to check for linear relationship. For example, you can use scatter plots and then visually check for linearity. If the relationship displayed in your scatter plot is not linear, then you need to use nonlinear regression. This concludes our video. Thanks for watching. Hello and welcome. In this video, we'll be covering nonlinear regression basics. So let's get started. These data points correspond to China's gross domestic product, or GDP, from 1960 to 2014. The first column is the years, and the second is China's corresponding annual gross domestic income in US dollars for that year. This is what the data points look like. Now, we have a couple of interesting questions. First, can GDP be predicted based on time? And second, can we use a simple linear regression to model it? Indeed, if the data shows a curvy trend, then linear regression will not produce very accurate results when compared to a nonlinear regression, simply because, as the name implies, linear regression presumes that the data is linear. The scatter plot shows that there seems to be a strong relationship between GDP and time, but the relationship is not linear. As you can see, the growth starts off slowly, then from 2005 onward, the growth is very significant. And finally, it decelerates slightly in the 2010s. It kind of looks like either a logistical or exponential function. So, it requires a special estimation method of the nonlinear regression procedure. For example, if we assume that the model for these data points are exponential functions, such as y hat equals theta 0 plus theta 1 theta 2 transpose x, or to the power of x, our job is to estimate the parameters of the model, i.e. thetas, and use the fitted model to predict GDP for unknown or future cases. In fact, many different regressions exist that can be used to fit whatever the data set looks like. You can see a quadratic and cubic regression lines here, and it can go on and on to infinite degrees. In essence, we can call all of these polynomial regression, where the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial in x. With many types of regression to choose from, there's a good chance that one will fit your data set well. Remember, it's important to pick a regression that fits the data the best. So, what is polynomial regression? Polynomial regression fits a curved line to your data. A simple example of polynomial with degree 3 is shown as y hat equals theta 0 plus theta 1x plus theta 2x squared plus theta 3x cubed, or to the power of 3, where thetas are parameters to be estimated that makes the model fit perfectly to the underlying data. Though the relationship between x and y is nonlinear here, and polynomial regression can fit them, a polynomial regression model can still be expressed as linear regression. I know it's a bit confusing, but let's look at an example. Given the third-degree polynomial equation, by defining x1 equals x and x2 equals x squared or x to the power of 2, and so on. The model is converted to a simple linear regression with new variables as y hat equals theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. This model is linear in the parameters to be estimated, right? Therefore, this polynomial regression is considered to be a special case of traditional multiple linear regression. So, you can use the same mechanism as linear regression to solve such a problem. Therefore, polynomial regression models can fit using the model of least squares. Least squares is a method for estimating the unknown parameters in a linear regression model by minimizing the sum of the squares of the differences between the observed dependent variable in the given dataset and those predicted by the linear function. So, what is nonlinear regression exactly? First, nonlinear regression is a method to model a nonlinear relationship between the dependent variable and a set of independent variables. Second, for a model to be considered nonlinear, y hat must be a nonlinear function of the parameters, theta, not necessarily the features x. When it comes to nonlinear equation, it can be the shape of exponential, logarithmic, and logistic, or many other types. As you can see in all of these equations, the change of y hat depends on changes in the parameters theta, not necessarily on x only. That is, in nonlinear regression, a model is nonlinear by parameters. In contrast to linear regression, we cannot use the ordinary least squares method to fit the data in nonlinear regression, and in general, estimation of the parameters is not easy. Let me answer two important questions here. First, how can I know if a problem is linear or nonlinear in an easy way? To answer this question, we have to do two things. The first is to visually figure out if the relation is linear or nonlinear. It's best to plot bivariate plots of output variables with each input variable. Also, you can calculate the correlation coefficient between independent and dependent variables, and if for all variables it is 0.7 or higher, there is a linear tendency, and thus it's not appropriate to fit a nonlinear regression. The second thing we have to do is to use nonlinear regression instead of linear regression when we cannot accurately model the relationship with linear parameters. The second important question is, how should I model my data if it displays nonlinear on a scatter plot? Well, to address this, you have to use either a polynomial regression, use a nonlinear regression model, or transform your data, which is not in scope for this course. Thanks for watching. Hello! In this video, we'll give you an introduction to classification. So let's get started. In machine learning, classification is a supervised learning approach, which can be thought of as a means of categorizing or classifying some unknown items into a discrete set of classes. Classification attempts to learn the relationship between a set of feature variables and a target variable of interest. The target attribute in classification is a categorical variable with discrete values. So, how does classification and classifiers work? Given a set of training data points along with the target labels, classification determines the class label for an unlabeled test case. Let's explain this with an example. A good sample of classification is the loan default prediction. Suppose a bank is concerned about the potential for loans not to be repaid. If previous loan default data can be used to predict which customers are likely to have problems repaying loans, these bad risk customers can either have their loan application declined or offered alternative products. The goal of a loan default predictor is to use existing loan default data, which is information about the customers, such as age, income, education, etc., to build a classifier, pass a new customer or potential future defaulter to the model, and then label it, i.e. the data points, as defaulter or not defaulter, or for example 0 or 1. This is how a classifier predicts an unlabeled test case. Please notice that this specific example was about a binary classifier with two values. We can also build classifier models for both binary classification and multi-class classification. For example, imagine that you've collected data about a set of patients, all of whom suffered from the same illness. During their course of treatment, each patient responded to one of 3 medications. You can use this labeled data set with a classification algorithm to build a classification model. Then you can use it to find out which drug might be appropriate for a future patient with the same illness. As you can see, it is a sample of multi-class classification. Classification has different business use cases as well. For example, to predict the category to which a customer belongs, for churn detection, where we predict whether a customer switches to another provider or brand, or to predict whether or not a customer responds to a particular advertising campaign. Data classification has several applications in a wide variety of industries. Essentially, many problems can be expressed as associations between feature and target variables, especially when labeled data is available. This provides a broad range of applicability for classification. For example, classification can be used for email filtering, speech recognition, handwriting recognition, biometric identification, document classification, and much more. Here we have the types of classification algorithms in machine learning. They include decision trees, naive Bayes, linear discriminant analysis, k-nearest neighbor, logistic regression, neural networks, and support vector machines. There are many types of classification algorithms. We will only cover a few in this course. Thanks for watching. Hello and welcome. In this video, we'll be covering the k-nearest neighbors algorithm. So let's get started. Imagine that a telecommunications provider has segmented its customer base by service usage patterns, categorizing the customers into 4 groups. If demographic data can be used to predict group membership, the company can customize offers for individual prospective customers. This is a classification problem. That is, given the data set with predefined labels, we need to build a model to be used to predict the class of a new or unknown case. The example focuses on using demographic data such as region, age, and marital status to predict usage patterns. The target field, called custcat, has 4 possible values that correspond to the 4 customer groups, as follows: basic service, e-service, plus service, and total service. Our objective is to build a classifier. For example, using the rows 0 to 7 to predict the class of row 8. We will use a specific type of classification called k-nearest neighbor. Just for sake of demonstration, let's use only 2 fields as predictors, specifically age and income, and then plot the customers based on their group membership. Now, let's say that we have a new customer, for example, record number 8, with a known age and income. How can we find the class of this customer? Can we find one of the closest cases and assign the same class label to our new customer? Can we also say that the class of our new customer is most probably group 4, i.e. total service, because its nearest neighbor is also of class 4? Yes, we can. In fact, it is the first nearest neighbor. Now, the question is, to what extent can we trust our judgment, which is based on the first nearest neighbor? It might be a poor judgment, especially if the first nearest neighbor is a very specific case or an outlier, correct? Now, let's look at our scatter plot again. Rather than choose the first nearest neighbor, what if we chose the 5 nearest neighbors and did a majority vote among them to define the class of our new customer? In this case, we'd see that 3 out of 5 nearest neighbors tell us to go for class 3, which is plus service. Doesn't this make more sense? Yes, in fact, it does. In this case, the value of k in the k-nearest neighbors algorithm is 5. This example highlights the intuition behind the k-nearest neighbors algorithm. Now, let's define the k-nearest neighbors. The k-nearest neighbors algorithm is a classification algorithm that takes a bunch of labeled points and uses them to learn how to label other points. This algorithm classifies cases based on their similarity to other cases. In k-nearest neighbors, data points that are near each other are said to be neighbors. K-nearest neighbors is based on this paradigm. Similar cases with the same class labels are near each other. Thus, the distance between 2 cases is a measure of their dissimilarity. There are different ways to calculate the similarity, or conversely, the distance or dissimilarity of 2 data points. For example, this can be done using Euclidean distance. Now, let's see how the k-nearest neighbors algorithm actually works. In a classification problem, the k-nearest neighbors algorithm works as follows. 1. Pick a value for k. 2. Calculate the distance from the new case. Hold out from each of the cases in the dataset. 3. Search for the k observations in the training data that are nearest to the measurements of the unknown data point. And 4. Predict the response of the unknown data point using the most popular response value from the k nearest neighbors. There are 2 parts in this algorithm that might be a bit confusing. First, how to select the correct k, and second, how to compute the similarity between cases, for example, among customers. Let's first start with the second concern. That is, how can we calculate the similarity between 2 data points? Assume that we have 2 customers, customer 1 and customer 2. And for a moment, assume that these 2 customers have only one feature, age. We can easily use a specific type of Minkowski distance to calculate the distance of these 2 customers. It is indeed the Euclidean distance. Distance of x1 from x2 is root of 34 minus 30 to power of 2, which is 4. What about if we have more than one feature, for example, age and income? If we have income and age for each customer, we can still use the same formula, but this time we're using it in a 2-dimensional space. We can also use the same distance matrix for multi-dimensional vectors. Of course, we have to normalize our feature set to get the accurate dissimilarity measure. There are other dissimilarity measures as well that can be used for this purpose, but, as mentioned, it is highly dependent on data type and also the domain that classification is done for it. As mentioned, k in k nearest neighbors is the number of nearest neighbors to examine. It is supposed to be specified by the user. So, how do we choose the right k? Assume that we want to find the class of the customer noted as question mark on the chart. What happens if we choose a very low value of k? Let's say k equals 1. The first nearest point would be blue, which is class 1. This would be a bad prediction, since more of the points around it are magenta, or class 4. In fact, since its nearest neighbor is blue, we can say that we captured the noise in the data, or we chose one of the points that was an anomaly in the data. A low value of k causes a highly complex model as well, which might result in overfitting of the model. It means the prediction process is not generalized enough to be used for out-of-sample cases. Out-of-sample data is data that is outside of the dataset used to train the model. In other words, it cannot be trusted to be used for prediction of unknown samples. It's important to remember that overfitting is bad, as we want a general model that works for any data, not just the data used for training. Now, on the opposite side of the spectrum, if we choose a very high value of k, such as k equals 20, then the model becomes overly generalized. So, how can we find the best value for k? The general solution is to reserve a part of your data for testing the accuracy of the model. Once you've done so, choose k equals 1 and then use the training part for modeling and calculate the accuracy of prediction using all samples in your test set. Repeat this process, increasing the k, and see which k is best for your model. For example, in our case, k equals 4 will give us the best accuracy. Nearest neighbors analysis can also be used to compute values for a continuous target. In this situation, the average or median target value of the nearest neighbors is used to obtain the predicted value for the new case. For example, assume that you are predicting the price of a home based on its feature set, such as number of rooms, square footage, the year it was built, and so on. You can easily find the 3 nearest neighbor houses, of course, not only based on distance, but also based on all the attributes, and then predict the price of the house as the median of neighbors. This concludes this video. Thanks for watching. Hello and welcome. In this video, we'll be covering evaluation metrics for classifiers. So let's get started. Evaluation metrics explain the performance of a model. Let's talk more about the model evaluation metrics that are used for classification. Imagine that we have an historical data set which shows the customer churn for a telecommunication company. We have trained the model, and now we want to calculate its accuracy using the test set. We pass the test set to our model, and we find the predicted labels. Now the question is, how accurate is this model? Basically, we compare the actual values in the test set with the values predicted by the model to calculate the accuracy of the model. Evaluation metrics provide a key role in the development of a model as they provide insight to areas that might require improvement. There are different model evaluation metrics, but we just talk about 3 of them here. Specifically, Jaccard Index, F1 score, and log loss. Let's first look at one of the simplest accuracy measurements, the Jaccard Index, also known as the Jaccard Similarity Coefficient. Let's say Y shows the true labels of the churn dataset, and Y hat shows the predicted values by our classifier. Then we can define Jaccard as the size of the intersection divided by the size of the union of 2 label sets. For example, for a test set of size 10 with 8 correct predictions or 8 intersections, the accuracy by the Jaccard Index would be 0.66. If the entire set of predicted labels for a sample strictly matches with the true set of labels, then the subset accuracy is 1.0. Otherwise, it is 0.0. Another way of looking at accuracy of classifiers is to look at a confusion matrix. For example, let's assume that our test set has only 40 rows. This matrix shows the corrected and wrong predictions in comparison with the actual labels. Each confusion matrix row shows the actual true labels in the test set, and the columns show the predicted labels by classifier. Let's look at the first row. The first row is for customers whose actual churn value in the test set is 1. As you can calculate, out of 40 customers, the churn value of 15 of them is 1. And out of these 15, the classifier correctly predicted 6 of them as 1 and 9 of them as 0. This means that for 6 customers, the actual churn value was 1 in the test set, and the classifier also correctly predicted those as 1. However, while the actual label of 9 customers was 1, the classifier predicted those as 0, which is not very good. We can consider this as an error of the model for the first row. What about the customers with a churn value 0? Let's look at the second row. It looks like there were 25 customers whose churn value was 0. The classifier correctly predicted 24 of them as 0, and 1 of them wrongly predicted as 1. So, it has done a good job in predicting the customers with a churn value of 0. A good thing about the confusion matrix is that it shows the model's ability to correctly predict or separate the classes. In the specific case of a binary classifier, such as this example, we can interpret these numbers as the count of true positives, false negatives, true negatives, and false positives. Based on the count of each section, we can calculate the precision and recall of each label. Precision is a measure of the accuracy, provided that a class label has been predicted. It is defined by precision equals true positive divided by true positive plus false positive. And recall is the true positive rate. It is defined as recall equals true positive divided by true positive plus false negative. So, we can calculate the precision and recall of each class. Now we're in the position to calculate the F1 scores for each label based on the precision and recall of that label. The F1 score is the harmonic average of the precision and recall, where an F1 score reaches its best value at 1, which represents perfect precision and recall, and its worst at 0. It is a good way to show that a classifier has a good value for both recall and precision. It is defined using the F1 score equation. For example, the F1 score for class 0, i.e. churn equals 0, is 0.83, and the F1 score for class 1, i.e. churn equals 1, is 0.55. And finally, we can tell the average accuracy for this classifier is the average of the F1 score for both labels, which is 0.72 in our case. Please notice that both Jacquard and F1 score can be used for multi-class classifiers as well, which is out of scope for this course. Now let's look at another accuracy metric for classifiers. Sometimes the output of a classifier is the probability of a class label instead of the label. For example, in logistic regression, the output can be the probability of customer churn, i.e. yes, or equals to 1. This probability is a value between 0 and 1. Logarithmic loss, also known as log loss, measures the performance of a classifier where the predicted output is a probability value between 0 and 1. So, for example, predicting a probability of 0.13 when the actual label is 1 would be bad and would result in a high log loss. We can calculate the log loss for each row using the log loss equation, which measures how far each prediction is from the actual label. Then we calculate the average log loss across all rows of the test set. It is obvious that ideal classifiers have progressively smaller values of log loss, so the classifier with the lower log loss has better accuracy. Thanks for watching. Hello and welcome. In this video, we're going to introduce and examine decision trees. So let's get started. What exactly is a decision tree? How do we use them to help us classify? How can I grow my own decision tree? These may be some of the questions that you have in mind from hearing the term decision tree. Hopefully, you'll soon be able to answer these questions and many more by watching this video. Imagine that you're a medical researcher compiling data for a study. You've already collected data about a set of patients, all of whom suffered from the same illness. During their course of treatment, each patient responded to one of two medications. We'll call them drug A and drug B. Part of your job is to build a model to find out which drug might be appropriate for a future patient with the same illness. The feature sets of this data set are age, gender, blood pressure, and cholesterol of our group of patients. And the target is the drug that each patient responded to. It is a sample of binary classifiers, and you can use the training part of the data set to build a decision tree, and then use it to predict the class of an unknown patient. In essence, to come up with a decision on which drug to prescribe to a new patient. Let's see how a decision tree is built for this data set. Decision trees are built by splitting the training set into distinct nodes, where one node contains all of, or most of, one category of the data. If we look at the diagram here, we can see that it's a patient's classifier. So, as mentioned, we want to prescribe a drug to a new patient, but the decision to choose drug A or B will be influenced by the patient's situation. We start with age, which can be young, middle-aged, or senior. If the patient is middle-aged, then we'll definitely go for drug B. On the other hand, if he is a young or a senior patient, we'll need more details to help us determine which drug to prescribe. The additional decision variables can be things such as cholesterol levels, gender, or blood pressure. For example, if the patient is female, then we will recommend drug A. But if the patient is male, then we'll go for drug B. As you can see, decision trees are about testing an attribute and branching the cases based on the result of the test. Each internal node corresponds to a test, and each branch corresponds to a result of the test, and each leaf node assigns a patient to a class. Now the question is, how can we build such a decision tree? Here is the way that a decision tree is built. A decision tree can be constructed by considering the attributes one by one. First, choose an attribute from our dataset. Calculate the significance of the attribute in the splitting of the data. In the next video, we will explain how to calculate the significance of an attribute to see if it's an effective attribute or not. Next, split the data based on the value of the best attribute. Then, go to each branch and repeat it for the rest of the attributes. After building this tree, you can use it to predict the class of unknown cases, or, in our case, the proper drug for a new patient based on his or her characteristics. This concludes this video. Thanks for watching. Hello and welcome. In this video, we'll be covering the process of building decision trees. So let's get started. Consider the drug dataset again. The question is, how do we build a decision tree based on that dataset? Decision trees are built using recursive partitioning to classify the data. Let's say we have 14 patients in our dataset. The algorithm chooses the most predictive feature to split the data on. What is important in making a decision tree is to determine which attribute is the best or more predictive to split data based on the feature. Let's say we pick cholesterol as the first attribute to split data. It will split our data into two branches. As you can see, if the patient has high cholesterol, we cannot say with high confidence that drug B might be suitable for him. Also, if the patient's cholesterol is normal, we still don't have sufficient evidence or information to determine if either drug A or drug B is in fact suitable. It is a sample of bad attribute selection for splitting data. So, let's try another attribute. Again, we have our 14 cases. This time, we pick the sex attribute of patients. It will split our data into two branches, male and female. As you can see, if the patient is female, we can say drug B might be suitable for her with high certainty. But if the patient is male, we don't have sufficient evidence or information to determine if drug A or drug B is suitable. However, it is still a better choice in comparison with the cholesterol attribute because the result in the nodes are more pure. It means nodes that are either mostly drug A or drug B. So, we can say the sex attribute is more significant than cholesterol, or in other words, it's more predictive than the other attributes. Indeed, predictiveness is based on decrease in impurity of nodes. We're looking for the best feature to decrease the impurity of patients in the leaves after splitting them up based on that feature. So, the sex feature is a good candidate in the following case because it almost found the pure patients. Let's go one step further. For the male patient branch, we again test other attributes to split the subtree. We test cholesterol again here. As you can see, it results in even more pure leaves. So we can easily make a decision here. For example, if a patient is male and his cholesterol is high, we can certainly prescribe drug A. But if it is normal, we can prescribe drug B with high confidence. As you might notice, the choice of attribute to split data is very important, and it is all about purity of the leaves after the split. A node in the tree is considered pure if, in 100% of the cases, the nodes fall into a specific category of the target field. In fact, the method uses recursive partitioning to split the training records into segments by minimizing the impurity at each step. Impurity of nodes is calculated by entropy of data in the node. So, what is entropy? Entropy is the amount of information disorder, or the amount of randomness in the data. The entropy in the node depends on how much random data is in that node and is calculated for each node. In decision trees, we're looking for trees that have the smallest entropy in their nodes. The entropy is used to calculate the homogeneity of the samples in that node. If the samples are completely homogeneous, the entropy is 0, and if the samples are equally divided, it has an entropy of 1. This means if all the data in a node are either drug A or drug B, then the entropy is 0. But if half of the data are drug A and other half are B, then the entropy is 1. You can easily calculate the entropy of a node using the frequency table of the attribute through the entropy formula, where P is for the proportion or ratio of a category, such as drug A or B. Please remember, though, that you don't have to calculate these, as it's easily calculated by the libraries or packages that you use. As an example, let's calculate the entropy of the dataset before splitting it. We have 9 occurrences of drug B and 5 of drug A. You can embed these numbers into the entropy formula to calculate the impurity of the target attribute before splitting it. In this case, it is 0.94. So, what is entropy after splitting? Now we can test different attributes to find the one with the most predictiveness, which results in 2 more pure branches. Let's first select the cholesterol of the patient and see how the data gets split based on its values. For example, when it is normal, we have 6 for drug B and 2 for drug A. We can calculate the entropy of this node based on the distribution of drug A and B, which is 0.8 in this case. But when cholesterol is high, the data is split into 3 for drug B and 3 for drug A. Calculating its entropy, we can see it would be 1.0. We should go through all the attributes and calculate the entropy after the split, and then choose the best attribute. Okay, let's try another field. Let's choose the sex attribute for the next check. As you can see, when we use the sex attribute to split the data, when its value is female, we have 3 patients that responded to drug B and 4 patients that responded to drug A. The entropy for this node is 0.98, which is not very promising. However, on the other side of the branch, when the value of the sex attribute is male, the result is more pure, with 6 for drug B and only 1 for drug A. The entropy for this group is 0.59. Now, the question is, between the cholesterol and sex attributes, which one is a better choice? Which one is better at the first attribute to divide the dataset into 2 branches? Or, in other words, which attribute results in more pure nodes for our drugs? Or in which tree do we have less entropy after splitting rather than before splitting? The sex attribute with entropy of 0.98 and 0.59, or the cholesterol attribute with entropy of 0.81 and 1.0 in its branches? The answer is the tree with the higher information gain after splitting. So, what is information gain? Information gain is the information that can increase the level of certainty after splitting. It is the entropy of a tree before the split minus the weighted entropy after the split by an attribute. we can think of information gain and entropy as opposites. As entropy, or the amount of randomness, decreases, the information gain, or amount of certainty, increases, and vice versa. So, constructing a decision tree is all about finding attributes that return the highest information gain. Let's see how information gain is calculated for the sex attribute. As mentioned, the information gain is the entropy of the tree before the split minus the weighted entropy after the split. The entropy of the tree before the split is 0.94. The portion of female patients is 7 out of 14, and its entropy is 0.985. Also, the portion of men is 7 out of 14, and the entropy of the male node is 0.592. The result of a square bracket here is the weighted entropy after the split. So, the information gain of the tree, if we use the sex attribute to split the dataset, is 0.151. As you can see, we will consider the entropy over the distribution of samples falling under each leaf node, and we'll take a weighted average of that entropy, weighted by the proportion of samples falling under that leaf. We can calculate the information gain of the tree if we use cholesterol as well. It is 0.48. Now, the question is, which attribute is more suitable? Well, as mentioned, the tree with the higher information gain after splitting. This means the sex attribute. So, we select the sex attribute as the first splitter. Now, what is the next attribute after branching by the sex attribute? Well, as you can guess, we should repeat the process for each branch and test each of the other attributes to continue to reach the most pure leaves. This is the way you build a decision tree. Thanks for watching. Hello and welcome. In this video, we'll learn a machine learning method called logistic regression, which is used for classification. In examining this method, we'll specifically answer these three questions. What is logistic regression? What kind of problems can be solved by logistic regression? And in which situations do we use logistic regression? So let's get started. Logistic regression is a statistical and machine learning technique for classifying records of a dataset based on the values of the input fields. Let's say we have a telecommunication dataset that we'd like to analyze in order to understand which customers might leave us next month. This is historical customer data where each row represents one customer. Imagine that you're an analyst at this company, and you have to find out who is leaving and why. You'll use the dataset to build a model based on historical records and use it to predict the future churn within the customer group. The dataset includes information about services that each customer has signed up for, customer account information, demographic information about customers, like gender and age range, and also customers who've left the company within the last month. The column is called churn. We can use logistic regression to build a model for predicting customer churn using the given features. In logistic regression, we use one or more independent variables such as tenure, age, and income to predict an outcome, such as churn, which we call a dependent variable, representing whether or not customers will stop using the service. Logistic regression is analogous to linear regression, but tries to predict a categorical or discrete target field instead of a numeric one. In linear regression, we might try to predict a continuous value of variables such as the price of a house, blood pressure of a patient, or fuel consumption of a car. But in logistic regression, we predict a variable which is binary, such as yes, no, true, false, successful or not successful, pregnant, not pregnant, and so on, all of which can be coded as 0 or 1. In logistic regression, independent variables should be continuous. If categorical, they should be dummy or indicator coded. This means we have to transform them to some continuous value. Please note that logistic regression can be used for both binary classification and multi-class classification, but for simplicity, in this video, we'll focus on binary classification. Let's examine some applications of logistic regression before we explain how they work. As mentioned, logistic regression is a type of classification algorithm, so it can be used in different situations. For example, to predict the probability of a person having a heart attack within a specified time period, based on our knowledge of the person's age, sex, and body mass index. Or to predict the chance of mortality in an injured patient, or to predict whether a patient has a given disease, such as diabetes, based on observed characteristics of that patient, such as weight, height, blood pressure, and results of various blood tests, and so on. In a marketing context, we can use it to predict the likelihood of a customer purchasing a product or halting a subscription, as we've done in our churn example. We can also use logistic regression to predict the probability of failure of a given process, system, or product. We can even use it to predict the likelihood of a homeowner defaulting on a mortgage. These are all good examples of problems that can be solved using logistic regression. Notice that in all these examples, not only do we predict the class of each case, we also measure the probability of a case belonging to a specific class. There are different machine algorithms which can classify or estimate a variable. The question is, when should we use logistic regression? Here are 4 situations in which logistic regression is a good candidate. First, when the target field in your data is categorical or specifically is binary, such as 0, 1, yes, no, churn or no churn, positive, negative, and so on. Second, you need the probability of your prediction. For example, if you want to know what the probability is of a customer buying a product. Logistic regression returns a probability score between 0 and 1 for a given sample of data. In fact, logistic regression predicts the probability of that sample, and we map the cases to a discrete class based on that probability. Third, if your data is linearly separable. The decision boundary of logistic regression is a line, or a plane, or a hyperplane. A classifier will classify all the points on one side of the decision boundary as belonging to one class, and all those on the other side as belonging to the other class. For example, if we have just 2 features and are not applying any polynomial processing, we can obtain an inequality like theta 0 plus theta 1x1 plus theta 2x2 is greater than 0, which is a half-plane, easily plottable. Please note that in using logistic regression, we can also achieve a complex decision boundary using polynomial processing as well, which is out of scope here. You'll get more insight from decision boundaries when you understand how logistic regression works. Fourth, you need to understand the impact of a feature. You can select the best features based on the statistical significance of the logistic regression model coefficients or parameters. That is, after finding the optimum parameters, a feature X with the weight theta 1 close to 0 has a smaller effect on the prediction than features with large absolute values of theta 1. Indeed, it allows us to understand the impact an independent variable has on the dependent variable while controlling other independent variables. Let's look at our dataset again. We define the independent variables as x and dependent variable as y. Notice that for the sake of simplicity, we can code the target or dependent values to 0 or 1. The goal of logistic regression is to build a model to predict the class of each sample, which in this case is a customer, as well as the probability of each sample belonging to a class. Given that, let's start to formalize the problem. X is our data set, in the space of real numbers of m by n, that is, of m dimensions or features and n records. And y is the class that we want to predict, which can be either 0 or 1. Ideally, a logistic regression model, so-called y-hat, can predict that the class of the customer is 1, given its features x. It can also be shown quite easily that the probability of a customer being in class 0 can be calculated as 1 minus the probability that the class of the customer is 1. Thanks for watching this video. Hello and welcome. In this video, we'll learn more about training a logistic regression model. Also, we'll be discussing how to change the parameters of the model to better estimate the outcome. Finally, we talk about the cost function and gradient descent in logistic regression as a way to optimize the model. So let's start. The main objective of training in logistic regression is to change the parameters of the model so as to be the best estimation of the labels of the samples in the dataset. For example, the customer churn. How do we do that? In brief, first we have to look at the cost function and see what the relation is between the cost function and the parameters theta. So, we should formulate the cost function. Then, using the derivative of the cost function, we can find how to change the parameters to reduce the cost, or rather, the error. Let's dive into it to see how it works. But before I explain it, I should highlight for you that it needs some basic mathematical background to understand it. However, you shouldn't worry about it, as most data science languages like Python, R, and Scala have some packages or libraries that calculate these parameters for you. So, let's take a look at it. Let's first find the cost function equation for a sample case. To do this, we can use one of the customers in the churn problem. There's normally a general equation for calculating the cost. The cost function is the difference between the actual values of y and our model output, y-hat. This is a general rule for most cost functions in machine learning. We can show this as the cost of our model comparing it with actual labels, which is the difference between the predicted value of our model and actual value of the target field, where the predicted value of our model is sigmoid of theta transpose x. Usually, the square of this equation is used because of the possibility of the negative result, and for the sake of simplicity, half of this value is considered as the cost function through the derivative process. Now we can write the cost function for all the samples in our training set. For example, for all customers, we can write it as the average sum of the cost functions of all cases. It is also called the mean squared error, and as it is a function of a parameter vector theta, it is shown as j of theta. Okay, good. We have the cost function. Now, how do we find or set the best weights or parameters that minimize this cost function? The answer is, we should calculate the minimum point of this cost function, and it'll show us the best parameters for our model. Although we can find the minimum point of a function using the derivative of a function, there's not an easy way to find the global minimum point for such an equation. Given this complexity, describing how to reach the global minimum for this equation is outside the scope of this video. So, what is the solution? Well, we should find another cost function instead, one which has the same behavior but is easier to find its minimum point. Let's plot the desirable cost function for our model. Recall that our model is y-hat. Our actual value is y, which equals 0 or 1, and our model tries to estimate it as we want to find a simple cost function for our model. For a moment, assume that our desired value for y is 1. This means our model is best if it estimates y equals 1. In this case, we need a cost function that returns 0 if the outcome of our model is 1, which is the same as the actual label. And the cost should keep increasing as the outcome of our model gets farther from 1. And cost should be very large if the outcome of our model is close to 0. We can see that the minus log function provides such a cost function for us. It means if the actual value is 1 and the model also predicts 1, the minus log function returns 0 cost. But If the prediction is smaller than 1, the minus log function returns a larger cost value. So, we can use the minus log function for calculating the cost of our logistic regression model. So if you recall, we previously noted that in general, it is difficult to calculate the derivative of the cost function. Well, we can now change it with the minus log of our model. We can easily prove that in the case that desirable y is 1, the cost can be calculated as minus log y hat. And in the case that desirable y is 0, the cost can be calculated as minus log 1 minus y hat. Now we can plug it into our total cost function and rewrite it as this function. So, this is the logistic regression cost function. As you can see for yourself, it penalizes situations in which the class is 0 and the model output is 1, and vice versa. Remember, however, that y hat does not return a class as output, but it's a value of 0 or 1, which should be assumed as a probability. Now we can easily use this function to find the parameters of our model in such a way as to minimize the cost. Okay, let's recap what we've done. Our objective was to find a model that best estimates the actual labels. Finding the best model means finding the best parameters theta for that model. So the first question was, how do we find the best parameters for our model? Well, by finding and minimizing the cost function of our model. In other words, to minimize the j of theta we just defined. The next question is, how do we minimize the cost function? The answer is using an optimization approach. There are different optimization approaches, but we use one of the most famous and effective approaches here, gradient descent. The next question is, what is gradient descent? Generally, gradient descent is an iterative approach to finding the minimum of a function. Specifically in our case, gradient descent is a technique to use the derivative of a cost function to change the parameter values, to minimize the cost or error. Let's see how it works. The main objective of gradient descent is to change the parameter values so as to minimize the cost. How can gradient descent do that? Think of the parameters or weights in our model to be in a two-dimensional space. For example, theta 1, theta 2 for two feature sets, age and income. Recall the cost function, j, that we discussed in the previous slides. We need to minimize the cost function j, which is a function of variables theta 1 and theta 2. So let's add a dimension for the observed cost or error, j function. Let's assume that if we plot the cost function based on all possible values of theta 1, theta 2, we can see something like this. It represents the error value for different values of parameters, that is, error, which is a function of the parameters. This is called your error curve or error bowl of your cost function. Recall that we want to use this error bowl to find the best parameter values that result in minimizing the cost value. Now, the question is, which point is the best point for your cost function? Yes, you should try to minimize your position on the error curve. So what should you do? You have to find the minimum value of the cost by changing the parameters. But which way? Will you add some value to your weights or deduct some value? And how much would that value be? You can select random parameter values that locate a point on the bowl. You can think of our starting point being the yellow point. You change the parameters by delta theta 1 and delta theta 2 and take one step on the surface. Let's assume we go down one step in the bowl. As long as we're going downwards, we can go one more step. The steeper the slope, the further we can step. And we can keep taking steps. As we approach the lowest point, the slope diminishes, so we can take smaller steps until we reach a flat surface. This is the minimum point of our curve and the optimum theta 1, theta 2. What are these steps really? I mean, in which direction should we take these steps to make sure we descend? And how big should the steps be? To find the direction and size of these steps, in other words, to find how to update the parameters, you should calculate the gradient of the cost function at that point. The gradient is the slope of the surface at every point, and the direction of the gradient is the direction of the greatest uphill. Now the question is, how do we calculate the gradient of a cost function at a point? If you select a random point on this surface, for example the yellow point, and take the partial derivative of j of theta with respect to each parameter at that point, it gives you the slope of the move for each parameter at that point. Now, if we move in the opposite direction of that slope, it guarantees that we go down in the error curve. For example, if we calculate the derivative of j with respect to theta 1, we find out that it is a positive number. This indicates that function is increasing as theta 1 increases. So, to decrease j, we should move in the opposite direction. This means to move in the direction of the negative derivative for theta 1, i.e., slope. We have to calculate it for other parameters as well at each step. The gradient value also indicates how big of a step to take. If the slope is large, we should take a large step because we're far from the minimum. If the slope is small, we should take a smaller step. Gradient descent takes increasingly smaller steps towards the minimum with each iteration. The partial derivative of the cost function j is calculated using this expression. If you want to know how the derivative of the j function is calculated, you need to know the derivative concept, which is beyond our scope here. But to be honest, you don't really need to remember all the details about it, as you can easily use this equation to calculate the gradients. So, in a nutshell, this equation returns the slope of that point, and we should update the parameter in the opposite direction of the slope. A vector of all these slopes is the gradient vector, and we can use this vector to change or update all the parameters. We take the previous values of the parameters and subtract the error derivative. This results in the new parameters for theta that we know will decrease the cost. Also, we multiply the gradient value by a constant value mu, which is called the learning rate. Learning rate gives us additional control on how fast we move on the surface. In sum, we can simply say gradient descent is like taking steps in the current direction of the slope, and the learning rate is like the length of the step you take. So, these would be our new parameters. Notice that it's an iterative operation, and in each iteration, we update the parameters and minimize the cost until the algorithm converge is on an acceptable minimum. Okay, let's recap what we've done to this point by going through the training algorithm again, step by step. Step 1. We initialize the parameters with random values. Step 2. We feed the cost function with the training set and calculate the cost. We expect a high error rate as the parameters are set randomly. Step 3. We calculate the gradient of the cost function, keeping in mind that we have to use a partial derivative. So, to calculate the gradient vector, we need all the training data to feed the equation for each parameter. Of course, this is an expensive part of the algorithm, but there are some solutions for this. Step 4. We update the weights with new parameter values. Step 5. Here we go back to step 2 and feed the cost function again, which has new parameters. As was explained earlier, we expect less error as we're going down the error surface. We continue this loop until we reach a short value of cost or some limited number of iterations. Step 6. The parameters should be roughly found after some iterations. This means the model is ready, and we can use it to predict the probability of a customer staying or leaving. Thanks for watching this video. Hello and welcome! In this video, we will learn a machine learning method called Support Vector Machine, or SVM, which is used for classification. So let's get started. Imagine that you've obtained a dataset containing characteristics of thousands of human cell samples extracted from patients who were believed to be at risk of developing cancer. Analysis of the original data showed that many of the characteristics differed significantly between benign and malignant samples. You can use the values of these cell characteristics in samples from other patients to give an early indication of whether a new sample might be benign or malignant. You can use Support Vector Machine, or SVM, as a classifier to train your model to understand patterns within the data that might show benign or malignant cells. Once the model has been trained, it can be used to predict your new or unknown cell with rather high accuracy. Now, let me give you a formal definition of SVM. A support vector machine is a supervised algorithm that can classify cases by finding a separator. SVM works by first mapping data to a high-dimensional feature space so that data points can be categorized, even when the data are not otherwise linearly separable. Then, a separator is estimated for the data. The data should be transformed in such a way that a separator could be drawn as a hyperplane. For example, consider the following figure, which shows the distribution of a small set of cells only based on their unit size and clump thickness. As you can see, the data points fall into two different categories. It represents a linearly non-separable dataset. The two categories can be separated with a curve, but not a line. That is, it represents a linearly non-separable dataset, which is the case for most real-world datasets. We can transfer this data to a higher dimensional space, for example, mapping it to a three-dimensional space. After the transformation, the boundary between the two categories can be defined by a hyperplane. As we are now in three-dimensional space, the separator is shown as a plane. This plane can be used to classify new or unknown cases. Therefore, the SVM algorithm outputs an optimal hyperplane that categorizes new examples. Now, there are two challenging questions to consider. First, how do we transfer data in such a way that a separator could be drawn as a hyperplane? And two, how can we find the best or optimized hyperplane separator after transformation? Let's first look at transforming data to see how it works. For the sake of simplicity, imagine that our data set is one-dimensional data. This means we have only one feature X. As you can see, it is not linearly separable. So, what can we do here? Well, we can transfer it into a two-dimensional space. For example, you can increase the dimension of data by mapping X into a new space using a function with outputs X and X squared. Now the data is linearly separable, right? Notice that as we are in a two-dimensional space, the hyperplane is a line dividing a plane into two parts where each class lays on either side. Now we can use this line to classify new cases. Basically, mapping data into a higher dimensional space is called kerneling. The mathematical function used for the transformation is known as the kernel function and can be of different types, such as linear, polynomial, radial basis function, or RBF, and sigmoid. Each of these functions has its own characteristics, its pros and cons, and its equation. But the good news is that you don't need to know them, as most of them are already implemented in libraries of data science programming languages. Also, as there's no easy way of knowing which function performs best with any given dataset, we usually choose different functions in turn and compare the results. Now we get to another question. Specifically, how do we find the right or optimized separator after transformation? Basically, SVMs are based on the idea of finding a hyperplane that best divides a dataset into two classes, as shown here. As we're in a two-dimensional space, you can think of the hyperplane as a line that linearly separates the blue points from the red points. One reasonable choice as the best hyperplane is the one that represents the largest separation, or margin, between the two classes. So, the goal is to choose a hyperplane with as big a margin as possible. Examples closest to the hyperplane are support vectors. It is intuitive that only support vectors matter for achieving our goal, and thus, other training examples can be ignored. We try to find the hyperplane in such a way that it has the maximum distance to support vectors. Please note that the hyperplane and boundary decision lines have their own equations. So, finding the optimized hyperplane can be formalized using an equation which involves quite a bit more math, so I'm not going to go through it here in detail. That said, the hyperplane is learned from training data using an optimization procedure that maximizes the margin. And like many other problems, this optimization problem can also be solved by gradient descent, which is out of scope of this video. Therefore, the output of the algorithm is the values W and B for the line. You can make classifications using this estimated line. It is enough to plug in input values into the line equation. Then you can calculate whether an unknown point is above or below the line. If the equation returns a value greater than 0, then the point belongs to the first class, which is above the line, and vice versa. The two main advantages of support vector machines are that they're accurate in high-dimensional spaces, and they use a subset of training points in the decision function, called support vectors, so it's also memory efficient. The disadvantages of support vector machines include the fact that the algorithm is prone for overfitting if the number of features is much greater than the number of samples. Also, SVMs do not directly provide probability estimates, which are desirable in most classification problems. And finally, SVMs are not very efficient computationally if your dataset is very big, such as when you have more than 1,000 rows. And now our final question is, in which situation should I use SVM? Well, SVM is good for image analysis tasks, such as image classification and handwritten digit recognition. Also, SVM is very effective in text mining tasks, particularly due to its effectiveness in dealing with high-dimensional data. For example, it is used for detecting spam, text category assignment, and sentiment analysis. Another application of SVM is in gene expression data classification, again because of its power in high-dimensional data classification. SVM can also be used for other types of machine learning problems, such as regression, outlier detection, and clustering. I'll leave it to you to explore more about these particular problems. This concludes this video. Thanks for watching. Hello and welcome. In this video, we'll give you a high-level introduction to clustering, its applications, and different types of clustering algorithms. Let's get started. Imagine that you have a customer data set and you need to apply customer segmentation on this historical data. Customer segmentation is the practice of partitioning a customer base into groups of individuals that have similar characteristics. It is a significant strategy as it allows a business to target specific groups of customers so as to more effectively allocate marketing resources. For example, one group might contain customers who are high profit and low risk, that is, more likely to purchase products or subscribe for a service. Knowing this information allows a business to devote more time and attention to retaining these customers. Another group might include customers from nonprofit organizations, and so on. A general segmentation process is not usually feasible for large volumes of varied data. Therefore, you need an analytical approach to deriving segments and groups from large datasets. Customers can be grouped based on several factors, including age, gender, interests, spending habits, and so on. The important requirement is to use the available data to understand and identify how customers are similar to each other. Let's learn how to divide a set of customers into categories based on characteristics they share. One of the most adopted approaches that can be used for customer segmentation is clustering. Clustering can group data only unsupervised based on the similarity of customers to each other. It will partition your customers into mutually exclusive groups, for example, into 3 clusters. The customers in each cluster are similar to each other demographically. Now we can create a profile for each group, considering the common characteristics of each cluster. For example, the first group is made up of affluent and middle-aged customers. The second is made up of young, educated, and middle-income customers. And the third group includes young and low-income customers. Finally, we can assign each individual in our dataset to one of these groups or segments of customers. Now imagine that you cross-join this segmented dataset with the dataset of the product or services that customers purchase from your company. This information would really help to understand and predict the differences in individual customers' preferences and their buying behaviors across various products. Indeed, having this information would allow your company to develop highly personalized experiences for each segment. Customer segmentation is one of the popular usages of clustering. Cluster analysis also has many other applications in different domains. So let's first define clustering, and then we'll look at other applications. Clustering means finding clusters in a dataset unsupervised. So, what is a cluster? A cluster is a group of data points or objects in a dataset that are similar to other objects in the group and dissimilar to data points in other clusters. Now, the question is, what is different between clustering and classification? Let's look at our customer dataset again. Classification algorithms predict categorical class labels. This means assigning instances to predefined classes such as defaulted or non-defaulted. For example, if an analyst wants to analyze customer data in order to know which customers might default on their payments, she uses a labeled dataset as training data and uses classification approaches such as a decision tree, support vector machines or SVM, or logistic regression to predict the default value for a new or unknown customer. Generally speaking, classification is a supervised learning where each training data instance belongs to a particular class. In clustering, however, the data is unlabeled and the process is unsupervised. For example, we can use a clustering algorithm such as k-means to group similar customers as mentioned and assign them to a cluster based on whether they share similar attributes such as age, education, and so on. While I'll be giving you some examples in different industries, I'd like you to think about more samples of clustering. In the retail industry, clustering is used to find associations among customers based on their demographic characteristics, and use that information to identify buying patterns of various customer groups. Also, it can be used in recommendation systems to find a group of similar items or similar users and use it for collaborative filtering to recommend things like books or movies to customers. In banking, analysts find clusters of normal transactions to find the patterns of fraudulent credit card usage. Also, they use clustering to identify clusters of customers, for instance, to find loyal customers versus churn customers. In the insurance industry, clustering is used for fraud detection in claims analysis, or to evaluate the insurance risk of certain customers based on their segments. In publication media, clustering is used to auto-categorize news based on its content, or to tag news, then cluster it so as to recommend similar news articles to readers. In medicine, it can be used to characterize patient behavior based on their similar characteristics, so as to identify successful medical therapies for different illnesses. Or, in biology, clustering is used to group genes with similar expression patterns or to cluster genetic markers to identify family ties. If you look around, you can find many other applications of clustering, but generally, clustering can be used for one of the following purposes: exploratory data analysis, summary generation or reducing the scale, outlier detection, especially to be used for fraud detection or noise removal, finding duplicates in datasets, or as a pre-processing step for either prediction, other data mining tasks, or as part of a complex system. Let's briefly look at different clustering algorithms and their characteristics. Partition-based clustering is a group of clustering algorithms that produces sphere-like clusters, such as k-means, k-median, or fuzzy c-means. These algorithms are relatively efficient and are used for medium and large-size databases. Hierarchical clustering algorithms produce trees of clusters, such as agglomerative and divisive algorithms. This group of algorithms are very intuitive and are generally good for use with small-sized datasets. Density-based clustering algorithms produce arbitrary-shaped clusters. They are especially good when dealing with spatial clusters or when there is noise in your dataset. For example, the dbScan algorithm. This concludes our video. Thanks for watching. Hello and welcome. In this video, we'll be covering k-means clustering. So let's get started. Imagine that you have a customer data set and you need to apply customer segmentation on this historical data. Customer segmentation is the practice of partitioning a customer base into groups of individuals that have similar characteristics. One of the algorithms that can be used for customer segmentation is k-means clustering. K-means can group data only unsupervised, based on the similarity of customers to each other. Let's define this technique more formally. There are various types of clustering algorithms, such as partitioning, hierarchical, or density-based clustering. K-means is a type of partitioning clustering. That is, it divides the data into k non-overlapping subsets, or clusters, without any cluster internal structure or labels. This means it's an unsupervised algorithm. Objects within a cluster are very similar, and objects across different clusters are very different or dissimilar. As you can see, for using k-means, we have to find similar samples, for example, similar customers. Now we face a couple of key questions. First, how can we find the similarity of samples in clustering? And then, how do we measure how similar two customers are with regard to their demographics? Though the objective of k-means is to form clusters in such a way that similar samples go into a cluster and dissimilar samples fall into different clusters, it can be shown that instead of a similarity metric, we can use dissimilarity metrics. In other words, conventionally, the distance of samples from each other is used to shape the clusters. So, we can say k-means tries to minimize the intra-cluster distances and maximize the inter-cluster distances. Now, the question is, how can we calculate the dissimilarity or distance of two cases, such as two customers? Assume that we have two customers. We'll call them customer 1 and 2. Let's also assume that we have only one feature for each of these two customers, and that feature is age. We can easily use a specific type of Minkowski distance to calculate the distance of these two customers. Indeed, it is the Euclidean distance. What about if we have more than one feature, for example, age and income? For example, if we have income and age for each customer, we can still use the same formula, but this time in a two-dimensional space. Also, we can use the same distance matrix for multidimensional vectors. Of course, we have to normalize our feature set to get the accurate dissimilarity measure. There are other dissimilarity measures as well that can be used for this purpose, but it is highly dependent on data type and also the domain that clustering is done for it. For example, you may use Euclidean distance, cosine similarity, average distance, and so on. Indeed, the similarity measure highly controls how the clusters are formed, so it is recommended to understand the domain knowledge of your dataset and data type of features, and then choose the meaningful distance measurement. Now, let's see how k-means clustering works. For the sake of simplicity, let's assume that our dataset has only two features, the age and income of customers. This means it's a two-dimensional space. We can show the distribution of customers using a scatter plot. The y-axis indicates age, and the x-axis shows income of customers. We try to cluster the customer dataset into distinct groups, or clusters, based on these two dimensions. In the first step, we should determine the number of clusters. The key concept of the k-means algorithm is that it randomly picks a center point for each cluster. It means we must initialize k, which represents number of clusters. Essentially, determining the number of clusters in a dataset, or k, is a hard problem in k-means that we will discuss later. For now, let's put k equals 3 here for our sample dataset. It is like we have 3 representative points for our clusters. These 3 data points are called centroids of clusters and should be of same feature size of our customer feature set. There are 2 approaches to choose these centroids. 1. We can randomly choose 3 observations out of the dataset and use these observations as the initial means. Or 2, we can create 3 random points as centroids of the clusters, which is our choice that is shown in the plot with red color. After the initialization step, which was defining the centroid of each cluster, we have to assign each customer to the closest center. For this purpose, we have to calculate the distance of each data point, or in our case, each customer, from the centroid points. As mentioned before, depending on the nature of the data and the purpose for which clustering is being used, different measures of distance may be used to place items into clusters. Therefore, you will form a matrix where each row represents the distance of a customer from each centroid. It is called the distance matrix. The main objective of k-means clustering is to minimize the distance of data points from the centroid of its cluster and maximize the distance from other cluster centroids. So, in this step, we have to find the closest centroid to each data point. We can use the distance matrix to find the nearest centroid to data points. Finding the closest centroids for each data point, we assign each data point to that cluster. In other words, all the customers will fall to a cluster based on their distance from centroids. We can easily say that it does not result in good clusters because the centroids were chosen randomly from the first. Indeed, the model would have a high error. Here, error is the total distance of each point from its centroid. It can be shown as within cluster sum of squares error. Intuitively, we try to reduce this error. It means we should shape clusters in such a way that the total distance of all members of a cluster from its centroid be minimized. Now, the question is, how can we turn it into better clusters with less error? Okay, we move centroids. In the next step, each cluster center will be updated to be the mean for data points in its cluster. Indeed, each centroid moves according to their cluster members. In other words, the centroid of each of the 3 clusters becomes the new mean. For example, If point A coordination is 7.4 and 3.6, and point B features are 7.8 and 3.8, the new centroid of this cluster with 2 points would be the average of them, which is 7.6 and 3.7. Now we have new centroids. As you can guess, once again, we will have to calculate the distance of all points from the new centroids. The points are reclustered and the centroids move again. This continues until the centroids no longer move. Please note that whenever a centroid moves, each point's distance to the centroid needs to be measured again. Yes, k-means is an iterative algorithm, and we have to repeat steps 2 to 4 until the algorithm converges. In each iteration, it will move the centroids, calculate the distances from new centroids, and assign data points to the nearest centroid. It results in the clusters with minimum error or the most dense clusters. However, as it is a heuristic algorithm, there is no guarantee that it will converge to the global optimum, and the result may depend on the initial clusters. It means this algorithm is guaranteed to converge to a result, but the result may be a local optimum, i.e., not necessarily the best possible outcome. To solve this problem, it is common to run the whole process multiple times with different starting conditions. This means with randomized starting centroids, it may give a better outcome. And as the algorithm is usually very fast, it wouldn't be any problem to run it multiple times. Thanks for watching this video. Hello and welcome. In this video, we'll look at k-means accuracy and characteristics. Let's get started. Let's define the algorithm more concretely before we talk about its accuracy. A k-means algorithm works by randomly placing k-centroids, one for each cluster. The farther apart the clusters are placed, the better. The next step is to calculate the distance of each data point or object from the centroids. Euclidean distance is used to measure the distance from the object to the centroid. Please note, however, that you can also use different types of distance measurements, not just Euclidean distance. Euclidean distance is used because it's the most popular. Then, assign each data point or object to its closest centroid, creating a group. Next, once each data point has been classified to a group, recalculate the position of the k-centroids. The new centroid position is determined by the mean of all points in the group. Finally, this continues until the centroids no longer move. Now the question is, how can we evaluate the goodness of the clusters formed by k-means? In other words, how do we calculate the accuracy of k-means clustering? One way is to compare the clusters with the ground truth, if it's available. However, because k-means is an unsupervised algorithm, we usually don't have ground truth in real-world problems to be used. But there is still a way to say how bad each cluster is, based on the objective of the k-means. This value is the average distance between data points within a cluster. Also, average of the distances of data points from their cluster centroids can be used as a metric of error for the clustering algorithm. Essentially, determining the number of clusters in a dataset, or k as in the k-means algorithm, is a frequent problem in data clustering. The correct choice of k is often ambiguous because it's very dependent on the shape and scale of the distribution of points in a dataset. There are some approaches to address this problem, but one of the techniques that is commonly used is to run the clustering across the different values of k and looking at a metric of accuracy for clustering. This metric can be mean distance between data points and their cluster centroid, which indicate how dense our clusters are, or to what extent we minimize the error of clustering. Then, looking at the change of this metric, we can find the best value for k. But the problem is that with increasing the number of clusters, the distance of centroids to data points will always reduce. This means increasing k will always decrease the error. So, the value of the metric as a function of k is plotted and the elbow point is determined where the rate of decrease sharply shifts. It is the right k for clustering. This method is called the elbow method. So, let's recap k-means clustering. K-means is a partition-based clustering, which is A. Relatively efficient on medium and large-size datasets. B. Produces sphere-like clusters because the clusters are shaped around the centroids. And C. Its drawback is that we should pre-specify the number of clusters, and this is not an easy task. Thanks for watching. Hello and welcome! In this video, we'll be covering hierarchical clustering. So let's get started. Let's look at this chart. An international team of scientists led by UCLA biologists use this dendrogram to report genetic data from more than 900 dogs from 85 breeds and more than 200 wild gray wolves worldwide, including populations from North America, Europe, the Middle East, and East Asia. They use molecular genetic techniques to analyze more than 48,000 genetic markers. This diagram shows hierarchical clustering of these animals based on the similarity in their genetic data. Hierarchical clustering algorithms build a hierarchy of clusters where each node is a cluster consisting of the clusters of its daughter nodes. Strategies for hierarchical clustering generally fall into two types, divisive and agglomerative. Divisive is top-down, so you start with all observations in a large cluster and break it down into smaller pieces. Think about divisive as dividing the cluster. Agglomerative is the opposite of divisive, so it is bottom-up, where each observation starts in its own cluster and pairs of clusters are merged together as they move up the hierarchy. Agglomeration means to amass or collect things, which is exactly what this does with the cluster. The agglomerative approach is more popular among data scientists, and so it is the main subject of this video. Let's look at a sample of agglomerative clustering. This method builds the hierarchy from the individual elements by progressively merging clusters. In our example, let's say we want to cluster 6 cities in Canada based on their distances from one another. They are Toronto, Ottawa, Vancouver, Montreal, Winnipeg, and Edmonton. We construct a distance matrix at this stage where the numbers in the row I, column J, is the distance between the I and J cities. In fact, this table shows the distances between each pair of cities. The algorithm is started by assigning each city to its own cluster. So, if we have 6 cities, we have 6 clusters, each containing just one city. Let's note each city by showing the first 2 characters of its name. The first step is to determine which cities, let's call them clusters from now on, to merge into a cluster. Usually we want to take the 2 closest clusters according to the chosen distance. Looking at the distance matrix, Montreal and Ottawa are the closest clusters. So we make a cluster out of them. Please notice that we just use a simple one-dimensional distance feature here, but our object can be multidimensional, and distance measurement can either be Euclidean, Pearson, average distance, or many others, depending on data type and domain knowledge. Anyhow, we have to merge these 2 closest cities in the distance matrix as well. So, rows and columns are merged as the cluster is constructed. As you can see in the distance matrix, rows and columns related to Montreal and Ottawa cities are merged as the cluster is constructed. Then, the distances from all cities to this new merged cluster get updated. But how? For example, how do we calculate the distance from Winnipeg to the Ottawa-Montreal cluster? Well, there are different approaches, but let's assume, for example, we just select the distance from the center of the Ottawa-Montreal cluster to Winnipeg. Updating the distance matrix, we now have one less cluster. Next, we look for the closest clusters once again. In this case, Ottawa, Montreal, and Toronto are the closest ones, which creates another cluster. In the next step, the closest distance is between the Vancouver cluster and the Edmonton cluster. Forming a new cluster, their data in the matrix table gets updated. Essentially, the rows and columns are merged as the clusters are merged and the distance updated. This is a common way to implement this type of clustering and has the benefit of caching distances between clusters. In the same way, agglomerative algorithm proceeds by merging clusters. And we repeat it until all clusters are merged and the tree becomes completed. It means until all cities are clustered into a single cluster of size 6. Hierarchical clustering is typically visualized as a dendrogram, as shown on this slide. Each merge is represented by a horizontal line. The y-coordinate of the horizontal line is the similarity of the two clusters that were merged, where cities are viewed as singleton clusters. By moving up from the bottom layer to the top node, a dendrogram allows us to reconstruct the history of merges that resulted in the depicted clustering. Essentially, hierarchical clustering does not require a pre-specified number of clusters. However, in some applications, we want a partition of disjoint clusters, just as in flat clustering. In those cases, the hierarchy needs to be cut at some point. For example, here, cutting in a specific level of similarity, we create 3 clusters of similar cities. This concludes this video. Thanks for watching. Hello and welcome. In this video, we'll be covering more details about hierarchical clustering. Let's get started. Let's look at agglomerative algorithm for hierarchical clustering. Remember that agglomerative clustering is a bottom-up approach. Let's say our data set has n data points. First, we want to create n clusters, one for each data point. Then, each point is assigned as a cluster. Next, we want to compute the distance proximity matrix, which will be an n by n table. After that, we want to iteratively run the following steps until the specified cluster number is reached, or until there is only one cluster left. First, merge the 2 nearest clusters. Distances are computed already in the proximity matrix. Second, update the proximity matrix with the new values. We stop after we've reached the specified number of clusters, or there is only one cluster remaining, with the results stored in a dendrogram. So, in the proximity matrix, we have to measure the distances between clusters and also merge the clusters that are nearest. So, the key operation is the computation of the proximity between the clusters with one point and also clusters with multiple data points. At this point, there are a number of key questions that need to be answered. For instance, how do we measure the distances between these clusters, and how do we define the nearest among clusters? We also can ask, which points do we use? First, let's see how to calculate the distance between 2 clusters with 1 point each. Let's assume that we have a data set of patients, and we want to cluster them using hierarchy clustering. So, our data points are patients with a feature set of 3 dimensions. For example, age, body mass index or BMI, and blood pressure. We can use different distance measurements to calculate the proximity matrix. For instance, Euclidean distance. So, if we have a data set of n patients, we can build an n by n dissimilarity distance matrix. It will give us the distance of clusters with one data point. However, as mentioned, we merge clusters in agglomerative clustering. Now the question is, how can we calculate the distance between clusters when there are multiple patients in each cluster? We can use different criteria to find the closest clusters and merge them. In general, it completely depends on the data type, dimensionality of data, and most importantly, the domain knowledge of the dataset. In fact, different approaches to defining the distance between clusters distinguish the different algorithms. As you might imagine, there are multiple ways we can do this. The first one is called single linkage clustering. Single linkage is defined as the shortest distance between 2 points in each cluster, such as point A and B. Next up is complete linkage clustering. This time, we are finding the longest distance between the points in each cluster, such as the distance between point A and B. The third type of linkage is average linkage clustering, or the mean distance. This means we're looking at the average distance of each point from one cluster to every point in another cluster. The final linkage type to be reviewed is centroid linkage clustering. Centroid is the average of the feature sets of points in a cluster. This linkage takes into account the centroid of each cluster when determining the minimum distance. There are 3 main advantages to using hierarchical clustering. First, we do not need to specify the number of clusters required for the algorithm. Second, hierarchical clustering is easy to implement. And third, the dendrogram produced is very useful in understanding the data. There are some disadvantages as well. First, the algorithm can never undo any previous steps. So, for example, the algorithm clusters 2 points, and later on, we see that the connection was not a good one. The program cannot undo that step. Second, the time complexity for the clustering can result in very long computation times in comparison with efficient algorithms such as k-means. Finally, if we have a large data set, it can become difficult to determine the correct number of clusters by the dendrogram. Now, let's compare hierarchical clustering with k-means. K-means is more efficient for large data sets. In contrast to k-means, hierarchical clustering does not require the number of clusters to be specified. Hierarchical clustering gives more than one partitioning depending on the resolution, whereas k-means gives only one partitioning of the data. Hierarchical clustering always generates the same clusters, in contrast with k-means that returns different clusters each time it is run due to random initialization of centroids. Thanks for watching. Hello and welcome. In this video, we'll be covering dbScan, a density-based clustering algorithm which is appropriate to use when examining spatial data. So let's get started. Most of the traditional clustering techniques, such as k-means, hierarchical, and fuzzy clustering, can be used to group data in an unsupervised way. However, when applied to tasks with arbitrary shaped clusters or clusters within clusters, traditional techniques might not be able to achieve good results. That is, elements in the same cluster might not share enough similarity, or the performance may be poor. Additionally, while partitioning-based algorithms such as k-means may be easy to understand and implement in practice, the algorithm has no notion of outliers. That is, all points are assigned to a cluster even if they do not belong in any. In the domain of anomaly detection, this causes problems as anomalous points will be assigned to the same cluster as normal data points. The anomalous points pull the cluster centroid towards them, making it harder to classify them as anomalous points. In contrast, density-based clustering locates regions of high density that are separated from one another by regions of low density. Density in this context is defined as the number of points within a specified radius. A specific and very popular type of density-based clustering is dbSCAN. dbSCAN is particularly effective for tasks like class identification on a spatial context. The wonderful attribute of the dbSCAN algorithm is that it can find out any arbitrary shaped cluster without getting affected by noise. For example, this map shows the location of weather stations in Canada. dbSCAN can be used here to find the group of stations which show the same weather condition. As you can see, it not only finds different arbitrary shaped clusters, it can find the denser part of data-centered samples by ignoring less dense areas or noises. Now, let's look at this clustering algorithm to see how it works. dbSCAN stands for Density-Based Spatial Clustering of Applications with Noise. This technique is one of the most common clustering algorithms, which works based on density of object. dbSCAN works on the idea that if a particular point belongs to a cluster, it should be near to lots of other points in that cluster. It works based on two parameters, radius and minimum points. R determines a specified radius that, if it includes enough points within it, we call it a dense area. M determines the minimum number of data points we want in a neighborhood to define a cluster. Let's define radius as 2 units. For the sake of simplicity, assume it as radius of 2 centimeters around a point of interest. Also, let's set the minimum point, or M, to be 6 points, including the point of interest. To see how dbSCAN works, we have to determine the type of points. Each point in our dataset can be either a core, border, or outlier point. Don't worry, I'll explain what these points are in a moment. But the whole idea behind the dbSCAN algorithm is to visit each point and find its type first. Then we group points as clusters based on their types. Let's pick a point randomly. First, we check to see whether it's a core data point. So, what is a core point? A data point is a core point if, within our neighborhood of the point, there are at least m points. For example, as there are 6 points in the 2 centimeter neighbor of the red point, we mark this point as a core point. Okay, what happens if it's not a core point? Let's look at another point. Is this point a core point? No. As you can see, there are only 5 points in this neighborhood, including the yellow point. So what kind of point is this one? In fact, it is a border point. What is a border point? A data point is a border point if A, its neighborhood contains less than m data points, and B, it is reachable from some core point. Here, reachability means it is within our distance from a core point. It means that even though the yellow point is within the 2 centimeter neighborhood of the red point, it is not by itself a core point because it does not have at least 6 points in its neighborhood. We continue with the next point. As you can see, it is also a core point. And all points around it which are not core points are border points. Next core point, and next core point. Let's pick this point. You can see it is not a core point, nor is it a border point. So we label it as an outlier. What is an outlier? An outlier is a point that is not a core point and also is not close enough to be reachable from a core point. We continue and visit all the points in the dataset and label them as either core, border, or outlier. The next step is to connect core points that are neighbors and put them in the same cluster. So, a cluster is formed as at least one core point plus all reachable core points plus all their borders. It simply shapes all the clusters and finds outliers as well. Let's review this one more time to see why dbSCAN is cool. dbScan can find arbitrarily shaped clusters. It can even find a cluster completely surrounded by a different cluster. dbScan has a notion of noise and is robust to outliers. On top of that, dbScan makes it very practical for use in many real-world problems because it does not require one to specify the number of clusters, such as k in k-means. This concludes this video. Thanks for watching. Hello and welcome. In this video, we'll be going through a quick introduction to recommendation systems. So let's get started. Even though people's tastes may vary, they generally follow patterns. By that, I mean that there are similarities in the things that people tend to like. Or another way to look at it is that people tend to like things in the same category, or things that share the same characteristics. For example, if you've recently purchased a book on machine learning and Python, and you've enjoyed reading it, it's very likely that you'll also enjoy reading a book on data visualization. People also tend to have similar taste to those of the people they're close to in their lives. Recommender systems try to capture these patterns in similar behaviors to help predict what else you might like. Recommender systems have many applications that I'm sure you're already familiar with. Indeed, recommender systems are usually at play on many websites. For example, suggesting books on Amazon and movies on Netflix. In fact, everything on Netflix's website is driven by customer selection. If a certain movie gets viewed frequently enough, Netflix's recommender system ensures that that movie gets an increasing number of recommendations. Another example can be found in a daily use mobile app, where a recommender engine is used to recommend anything from where to eat or what job to apply to. On social media, sites like Facebook or LinkedIn regularly recommend friendships. Recommender systems are even used to personalize your experience on the web. For example, when you go to a news platform website, a recommender system will make note of the types of stories that you clicked on and make recommendations on which types of stories you might be interested in reading in future. There are many of these types of examples, and they are growing in number every day. So, let's take a closer look at the main benefits of using a recommendation system. One of the main advantages of using recommendation systems is that users get a broader exposure to many different products they might be interested in. This exposure encourages users towards continual usage or purchase of their product. Not only does this provide a better experience for the user, but it benefits the service provider as well, with increased potential revenue and better security for its customers. There are generally two main types of recommendation systems: content-based and collaborative filtering. The main difference between each can be summed up by the type of statement that a consumer might make. For instance, the main paradigm of a content-based recommendation system is driven by the statement, "Show me more of the same of what I've liked before." Content-based systems try to figure out what a user's favorite aspects of an item are, and then make recommendations on items that share those aspects. Collaborative filtering is based on a user saying, "Tell me what's popular among my neighbors because I might like it too." Collaborative filtering techniques find similar groups of users and provide recommendations based on similar tastes within that group. In short, it assumes that a user might be interested in what similar users are interested in. Also, there are hybrid recommender systems which combine various mechanisms. In terms of implementing recommender systems, there are two types: memory-based and model-based. In memory-based approaches, we use the entire user item dataset to generate a recommendation system. It uses statistical techniques to approximate users or items. Examples of these techniques include Pearson correlation, cosine similarity, and Euclidean distance, among others. In model-based approaches, a model of users is developed in an attempt to learn their preferences. Models can be created using machine learning techniques like regression, clustering, classification, and so on. This is the end of our video. Thanks for watching. Hello and welcome. In this video, we'll be covering content-based recommender systems. So let's get started. A content-based recommendation system tries to recommend items to users based on their profile. The user's profile revolves around that user's preferences and tastes. It is shaped based on user ratings, including the number of times that user has clicked on different items, or perhaps even liked those items. The recommendation process is based on the similarity between those items. Similarity, or closeness of items, is measured based on the similarity in the content of those items. When we say content, we're talking about things like the item's category, tag, genre, and so on. For example, if we have 4 movies, and if the user likes or rates the first 2 items, and if item 3 is similar to item 1 in terms of their genre, the engine will also recommend item 3 to the user. In essence, this is what content-based recommender system engines do. Now, let's dive into a content-based recommender system to see how it works. Let's assume we have a dataset of only 6 movies. This dataset shows movies that our user has watched and also the genre of each of the movies. For example, Batman vs. Superman is in the adventure superhero genre, and Guardians of the Galaxy is in the comedy, adventure, superhero, and science fiction genres. Let's say the user has watched and rated 3 movies so far, and she has given a rating of 2 out of 10 to the first movie, 10 out of 10 to the second movie, and 8 out of 10 to the third. The task of the recommender engine is to recommend one of the 3 candidate movies to this user. Or, in other words, we want to predict what the user's possible rating would be of the 3 candidate movies if she were to watch them. To achieve this, we have to build the user profile. First, we create a vector to show the user's ratings for the movies that she's already watched. We call it Input User Ratings. Then, we encode the movies through the one-hot encoding approach. Genre of movies are used here as a feature set. We use the first 3 movies to make this matrix, which represents the movie feature set matrix. If we multiply these 2 matrices, we can get the weighted feature set for the movies. Let's take a look at the result. This matrix is also called the weighted genre matrix and represents the interests of the user for each genre based on the movies that she's watched. Now, given the weighted genre matrix, we can shape the profile of our active user. Essentially, we can aggregate the weighted genres and then normalize them to find the user profile. It clearly indicates that she likes superhero movies more than other genres. We use this profile to figure out what movie is proper to recommend to this user. Recall that we also had 3 candidate movies for recommendation that haven't been watched by the user. We encode these movies as well. Now we're in the position where we have to figure out which of them is most suited to be recommended to the user. To do this, we simply multiply the user profile matrix by the candidate movie matrix, which results in the weighted movies matrix. It shows the weight of each genre with respect to the user profile. Now, if we aggregate these weighted ratings, we get the active user's possible interest level in these 3 movies. In essence, it's our recommendation list, which we can sort to rank the movies and recommend them to the user. For example, we can say that The Hitchhiker's Guide to the Galaxy has the highest score in our list and is proper to recommend to the user. Now you can come back and fill the predicted ratings for the user. So, to recap what we've discussed so far, the recommendation in a content-based system is based on users' taste and the content or feature set items. Such a model is very efficient. However, in some cases, it doesn't work. For example, assume that we have a movie in the drama genre, which the user has never watched. So, this genre would not be in her profile. Therefore, she'll only get recommendations related to genres that are already in her profile, and the recommender engine may never recommend any movie within other genres. This problem can be solved by other types of recommender systems, such as collaborative filtering. Thanks for watching. Hello and welcome. In this video, we'll be covering a recommender system technique called collaborative filtering. So let's get started. Collaborative filtering is based on the fact that relationships exist between products and people's interests. Many recommendation systems use collaborative filtering to find these relationships and to give an accurate recommendation of a product that the user might like or be interested in. Collaborative filtering has basically two approaches: user-based and item-based. User-based collaborative filtering is based on the user's similarity or neighborhood. Item-based collaborative filtering is based on similarity among items. Let's first look at the intuition behind the user-based approach. In user-based collaborative filtering, we have an active user for whom the recommendation is aimed. The collaborative filtering engine first looks for users who are similar. That is, users who share the active user's rating patterns. Collaborative filtering bases this similarity on things like history, preference, and choices that users make when buying, watching, or enjoying something. For example, movies that similar users have rated highly. Then it uses the ratings from these similar users to predict the possible ratings by the active user for a movie that she had not previously watched. For instance, if two users are similar, or are neighbors, in terms of their interest in movies, we can recommend a movie to the active user that her neighbor has already seen. Now, let's dive into the algorithm to see how all of this works. Assume that we have a simple user item matrix, which shows the ratings of 4 users for 5 different movies. Let's also assume that our active user has watched and rated 3 out of these 5 movies. Let's find out which of the 2 movies that our active user hasn't watched should be recommended to her. The first step is to discover how similar the active user is to the other users. How do we do this? Well, this can be done through several different statistical and vectorial techniques, such as distance or similarity measurements, including Euclidean distance, Pearson correlation, cosine similarity, and so on. To calculate the level of similarity between 2 users, we use the 3 movies that both the users have rated in the past. Regardless of what we use for similarity measurement, let's say, for example, the similarity could be 0.7, 0.9, and 0.4 between the active user and other users. These numbers represent similarity weights, or proximity of the active user to other users in the dataset. The next step is to create a weighted rating matrix. We just calculated the similarity of users to our active user in the previous slide. Now we can use it to calculate the possible opinion of the active user about our 2 target movies. This is achieved by multiplying the similarity weights to the user ratings. It results in a weighted ratings matrix, which represents the user's neighbor's opinion about our 2 candidate movies for recommendation. In fact, it incorporates the behavior of other users and gives more weight to the ratings of those users who are more similar to the active user. Now we can generate the recommendation matrix by aggregating all of the weighted rates. However, as 3 users rated the first potential movie and 2 users rated the second movie, we have to normalize the weighted rating values. We do this by dividing it by the sum of the similarity index for users. The result is the potential rating that our active user will give to these movies based on her similarity to other users. It is obvious that we can use it to rank the movies for providing recommendation to our active user. Now, let's examine what's different between user-based and item-based collaborative filtering. In the user-based approach, the recommendation is based on users of the same neighborhood, with whom he or she shares common preferences. For example, as user 1 and user 3 both liked item 3 and item 4, we consider them as similar or neighbor users, and recommend item 1, which is positively rated by user 1 to user 3. In the item-based approach, similar items build neighborhoods on the behavior of users. Please note, however, that it is not based on their contents. For example, item 1 and item 3 are considered neighbors, as they were positively rated by both user 1 and user 2. So, item 1 can be recommended to user 3 as he has already shown interest in item 3. Therefore, the recommendations here are based on the items in the neighborhood that a user might prefer. Collaborative filtering is a very effective recommendation system. However, there are some challenges with it as well. One of them is data sparsity. Data sparsity happens when you have a large data set of users who generally rate only a limited number of items. As mentioned, collaborative-based recommenders can only predict scoring of an item if there are other users who have rated it. Due to sparsity, we might not have enough ratings in the user item dataset, which makes it impossible to provide proper recommendations. Another issue to keep in mind is something called cold start. Cold start refers to the difficulty the recommendation system has when there is a new user, and as such, a profile doesn't exist for them yet. Cold start can also happen when we have a new item, which has not received a rating. Scalability can become an issue as well. As the number of users or items increases and the amount of data expands, collaborative filtering algorithms will begin to suffer drops in performance simply due to growth in the similarity computation. There are some solutions for each of these challenges, such as using hybrid-based recommender systems, but they are out of scope of this course. Thanks for watching.
Alright, before we start learning about Foursquare and their API, let's get some of the logistics out of the way. For this project, we will be using Watson Studio as the platform to build our code for the project and to share it with our peers. So each of you will need to create a Watson Studio account in order to proceed with the course. And in this video, I will walk you through the process. Now, for those of you who don't know, Watson Studio is an awesome platform that provides a suite of tools for data scientists to collaboratively and easily work with application developers and subject matter experts, and to build, train, and deploy models at scale. For the sake of this project, we won't be doing any extensive machine learning, but by using Watson Studio and learning about its features, you will hopefully appreciate what it has to offer. So let's go to the following link, that is www.ibm.com/cloud/Watson Studio. This will take you to the landing page of Watson Studio. Feel free to check it out to learn more about its features and what the platform has to offer. You can also watch the video to learn more about it. And once you're ready to create an account, you can simply click on Start Your Free Trial. This will bring you to a page where you have to enter your email address. So I'm going to do that. And then check the box to accept the terms. Once you've done that, click Next. This will redirect you to a page where you have to fill in your personal details. So go ahead and fill in your first and last name, your country or region, and a password for your account. Then you can check the box if you wish to remain informed about any products or services by IBM. And then scroll down and click Create Account. Awesome. So at this point, you should receive an email to confirm your account and to continue with the sign-up process. So go to your account and follow the instructions in the email. I'm going to do the same thing here. By the way, this is just a dummy account that I created for demonstration purposes. There you go. Here's the email from IBM Cloud. So you click on the email and you click Confirm Account. Awesome. You should automatically then get redirected to this page. Now this page has all the details about the IBM privacy policy, so feel free to read it to understand the policy and your rights as a user. Then scroll down all the way to the bottom and click Proceed. Here you can specify what account to use and the organization and the IBM Cloud space in case you have more than one. But for most of you, you can simply go with the default settings. So just click Continue. All right, now we'll take some time to create your account. There you go. And that completes the process of signing up on Watson Studio. Now you can click Get Started. Once you get to this page, you're good to go and you're good to start creating new projects. Now in the next video, I'll show you how to create a project and how to start creating notebooks under that project and how to share them with your peers or other collaborators. So I'll see you in the next video. Alright, so in this video, I will walk you through the process of creating a project on Watson Studio for this course, and I'll show you how to create notebooks under that project and how to share them with your peers, since your submissions in this course will be mainly notebooks shared from your Watson Studio account. So it's very important that you familiarize yourself with this process. So let's go to Watson Studio and log into your account. So when you click Sign In, you should land on this page. So this is the landing page of your account. Here you can see a summary, an overview of your account. For example, any projects that you created or are currently working on, any catalogs that you created, so you can organize your assets and your projects into catalogs, or any Watson services that you signed up for and you're currently using. But since you just created your account, then you shouldn't have any projects listed. So to create a project, you can simply click on the new project icon. So you click on that. Now Watson Studio supports different types of projects, ranging from very basic projects to very complicated ones involving deep learning and visual recognition and data engineering. And the beautiful thing about Watson Studio is that the environment for each project is prepped for you, meaning each project comes with a suite of tools and services pre-installed for your convenience, so you don't have to worry and spend time installing them. If you expect to use all of the different concepts shown here, then you can start a complete project. But in our case, we're simply analyzing neighborhood data, and we're not doing any extensive machine learning work. So creating a data science project should suffice. So let's click on Data Science and click OK. Now here, we get to name our project, and briefly describe it for our reference or for any collaborators who will be joining anytime in the future. So let's name our project Coursera_capstone and give it a brief description. I'm going to use Coursera capstone project analyzing neighborhood data. Now for this option, if you will be sharing your code with any external collaborator, which in this case you will, since you'll be sharing the code with your peers for peer evaluation and assessment, then you can uncheck this box in order to avoid any restriction on who you can share the project with. Now before we can proceed, we need to define our storage, where all of our files will be stored. This involves two steps. In the first step, we will create a storage service, and then in the second step, we'll have to come back and refresh for the service to appear. So let's do the first step now. So click on Add. All right, this page shows the storage service features and the different plans available. We will go with the default free plan, the light plan. It should be more than enough for this course. So click Create. You can go with the default settings and just click Confirm. There you go. So now the service has been created. We can go ahead and refresh for the service to appear. So click Refresh. There you go. And then scroll down and click Create. Awesome. So now the project has been created. So this is the overview page of the project. And now we can start creating notebooks to start building our code. The notebooks are referred to as assets to this project. So you can click on Add to Project and select Notebook from the drop-down menu. Now on this page, we can decide whether we want to create a blank notebook or a notebook from a file or a notebook from a URL. Now for this course, we're starting from scratch, so we'll have to create a blank notebook. So let's give it a name. I'm going to name it Capstone Intro Notebook, and you can give it a brief description. So I'm just going to say Capstone Project Demonstration Notebook. We'll be using a Python 3 kernel and the default server for runtime. So we scroll down and we click Create Notebook. It will take some time to initialize the notebook. All right, almost there. And there you go. Now, this is a typical Jupyter notebook, so all the notebook features can be used here. You can create markdown cells, for example. Let me go ahead and create a title and call this Capstone Project Notebook. Right, you can run code, so you can do mathematical operations. So 1 plus 1, 1 plus 2, it will give you the answer. You can execute a print statement. I am excited about this course. And one thing that's really cool about these notebooks is that if you have a cell that contains your credentials or other sensitive information, and you don't want to share that with either your peers or other collaborators, you can simply add a comment to that cell and it will hide the content. So what you would do, add a comment using @ hidden underscore cell. Let's say I define my credentials, that password. It's 1, 2, 3, 4, 5, right? So when you do that and you share the notebook, the content will be hidden. And I'll show you how the cell looks like after you share the notebook. All right, now to share your notebook, you have two options. There is direct share using a link to this notebook. And you do that by clicking the share icon. Right, so it opens this modal, and then you need to activate, sharing the notebook. And you have three options. You can either share only text and output, or you can share all the content excluding sensitive code cells, or you share the entire notebook including the code, right? So just to be safe, it's better to go with the second option. And it tells you what this option means. It means that you can exclude code cells containing sensitive data, right? And the way to share that notebook is you just copy this link and you paste it somewhere. So like you will paste it on the Coursera website where you'll be asked to share a link to the notebook, or you can email it or send it to any other collaborator you'll be working with. So this is the first option to share a notebook, right? Now, the other option, which is the one I like to use and recommend, is the option to share your notebook by publishing it to your GitHub repository. To do that, you will need to do two things. Number one, create a personal access token and add it to your Watson Studio account. And number two is to link your project to your GitHub repository. Now, before we create the personal access token, let me show you where you have to paste it. So go to your profile icon and select settings from the drop-down menu. Now, on your account settings page, select the integrations tab. And this is the field where you have to paste your personal access token. Now, to create this token, go to your GitHub account. Click on your profile image and select settings from the drop-down menu. And then on the left menu, select developer settings. And then personal access tokens. Click generate new token. Now give it a name. I'm going to use Capstone Project Token. And I'm going to give myself full access. Just going to select everything here. And then click generate token. Now make sure to copy this token, because as the message says here, you won't be able to see it again. So click on this copy icon. Now it's copied. Now go back to your Watson Studio account and paste the token. Now click save. And your GitHub account is now linked to your Watson Studio account. All right, so the next thing we have to do is to link the project to a GitHub repository. Now, you can either link it to an existing repository or to start a new and clean repository and use it exclusively for this capstone course. This is the option that I recommend. Now, you can easily do that by simply going to your GitHub account and by clicking on the @ sign next to your profile image or icon and selecting new repository from the drop-down menu. Now, give it a name. I'm going to name it Coursera Capstone Project. And make sure to check the box to initialize the repository with a README file. It's always a good practice to do that. And then click Create Repository. Awesome. So now that the repository is created, let's link our project to it. So let's go back to our Watson Studio account. Click on Projects. Now you should be able to find your project in the drop-down menu. So click on it and then go to the Settings tab. Now scroll down to the section that says Connect to a GitHub repository. And now enter the address to the repository. So mine and Coursera Capstone Project. All right, once you're done, hit connect. And now your project is linked to the GitHub repository. Now we should be able to simply push any work that we do, any code, any notebooks that we create to this GitHub repository. So let's go back to the notebook. So we close this. And I'll just go to the Assets tab. You should find your notebook under the Notebooks section. Click the Edit icon. And then to publish this notebook, click on the Publish icon and select Publish on GitHub. Now make sure that all the settings here are the ones that you're comfortable with. So make sure that all the content is published except for hidden code cells. And then click Publish. And that's it. Now you can go to your repository and view the notebook. So let's go to your GitHub account, refresh the page, and there you go. Now note two things. First, the commit comment says that the notebook was published from datascience.ibm.com. This means that your Watson Studio account was used to publish this notebook. Now, if you try to view the notebook, the hidden cell now shows the code was removed by DSX for sharing. Now, this is super convenient because instead of worrying about deleting cells with sensitive information, you can simply add the hidden cell comment, and that will prevent the content from being revealed to your peers or collaborators. And that's it for now. I'll see you in the next video.